Somewhere near the centre of our galaxy, floating silently in the vast emptiness of space, there's a massive molecular cloud, a thick region of gas and dust called Sagittarius B2. It's about 390 light-years from the supermassive black hole at the Milky Way's core, and in that strange interstellar cloud drifting billions of miles from anything remotely human is a molecule that seems oddly familiar. It's called ethyl formate. On Earth, it's known for two very specific things. It gives raspberries their flavour, and it's one of the molecules that creates the smell of rum. Let that sink in. There's a place in space where the chemistry of alcohol and berries floats in a frozen haze, not metaphorically, not poetically, but literally. The molecules that make those smells and tastes are out there, in the void. You could say the centre of our galaxy smells like a distillery in a fruit orchard, though you'd never want to visit. Sagittarius B2 isn't some minor puff of space dust. It's one of the largest molecular clouds ever observed, about 150 light-years wide, containing thousands of times more mass than our Sun, and it's crammed with all kinds of complex organic compounds. Ethyl formate is just one of the more crowd-pleasing discoveries. Astronomers didn't just stumble upon it by accident. They detected it using radio telescopes, specifically the IRAM 30-metre telescope in Spain. These instruments can analyse the light that passes through, or is emitted by a cloud like Sagittarius B2. Each molecule interacts with light in its own unique way, kind of like a fingerprint. Scientists scan the light spectrum for these chemical fingerprints and match them to known substances on Earth. That's how they confirmed ethyl formate, among over 50 other complex organic molecules, just floating out there in deep space. It's tempting to imagine this means there's rum and raspberry jam in orbit, but that's not quite how it works. The cloud is extremely cold, around +200 and these molecules are spread incredibly thinly. The density of the cloud is so low that even in such a massive volume, the actual concentration of molecules is tiny. If you flew through it in a spaceship, you wouldn't smell anything, but from a chemistry standpoint, the building blocks are absolutely there, and that's the part that really matters, not the smell or the taste, the chemistry. Because ethyl formate isn't just a fun trivia molecule, it's part of a much larger story. Its presence shows that complex organic chemistry happens naturally in space. It's one of many molecules that could play a role in the origin of life. If molecules like this are common throughout the galaxy, it suggests that the ingredients for life aren't confined to Earth. They're everywhere. Sagittarius B2 is essentially a giant cosmic kitchen. It's where new stars and planetary systems are being born, mixed in with this rich soup of prebiotic chemistry. And molecules like ethyl formate are just the start. Scientists have also found amino acid precursors, formamide, and other carbon-based compounds that are relevant to biology. All of them existing in extreme environments without any biological processes required to create them. This leads to some big questions. If nature can assemble the pieces of life on its own, in the dark, frozen heart of a nebula, then how common might life be? Are clouds like Sagittarius B2 the norm in star-forming regions? Are we looking at a galaxy that's primed for biology? It's still speculative, but it changes how we think about origins. Life may not be an Earth-only fluke. It may be something the universe does, just part of how stars and planets evolve. The discovery of these molecules also helps explain where Earth's own building blocks may have come from. One theory suggests that comets and asteroids, which formed in the early solar system and contain many of these same molecules, may have delivered them to Earth during the late heavy bombardment, a chaotic period when space rocks rained down on the young planet. So in a sense, the stuff in Sagittarius B2 could be part of our own ancestry. The bigger implication is that this kind of chemistry might be happening in every galaxy and every star-forming region, around stars very different from our own. It's not just Sagittarius B2. Other molecular clouds have revealed molecules like glycolaldehyde, a simple sugar, methyl cyanide and methanol, more evidence that complex organics are everywhere, and we're only scratching the surface. as telescopes get more powerful, like the James Webb Space Telescope, or the upcoming Extremely Large Telescope, ELT. We'll be able to study these clouds in more detail, at greater distances, and with higher sensitivity. What we find could completely rewrite our understanding of life's potential in the universe. But even if you strip away the astrobiology, the chemistry, the origins of life, it's still objectively strange and wonderful. In a galaxy filled with supernovae, black holes, and deathly radiation, we've found a patch of space that smells like rum and tastes like berries. You wouldn't survive even a second in Sagittarius B2. The cold, the vacuum, the radiation. It's about as hostile as the universe gets. But through the lens of a telescope, we've identified the comforting, Earth-like signature of flavour. It's like finding something familiar in a place that should be completely alien. That's why this fact sounds fake, but isn't. It's too weird, too specific, too oddly poetic to be true, and yet it is. So yes, out in the cosmic wilderness there's a place that smells like your favourite cocktail. Space is not just vast and violent, sometimes it's deliciously bizarre. Imagine a planet so dense, so carbon-rich, and under such intense pressure that its entire surface is likely covered in crystallized carbon. A literal diamond planet. It sounds like a sci-fi fantasy, like something you'd find in a movie about a billionaire space pirate. But this planet is real, and astronomers have found it. Meet 55 Cancri E, an exoplanet located about 41 light-years away in the constellation Cancer. It's a super-Earth, meaning it's a rocky planet larger than Earth but smaller than a gas giant. But size isn't what makes this planet jaw-dropping. It's what it's made of. The surface of 55 Cancri E may be rich in carbon, and due to the planet's mass, size, and proximity to its star, the conditions there are perfect for compressing that carbon into crystalline form. That's right, this planet could be composed largely of diamond. To understand why, you need to know how diamond forms. On Earth, diamond is created deep within the mantle, where carbon is subjected to pressures over 1 million times that of the atmosphere. The atoms are forced into a lattice structure, creating one of the hardest materials known. Now, scale that process up to an entire planet. 55 Cancri E is nearly twice the size of Earth, and has about 8 times its mass. That means the pressure inside it is immense, far greater than anything inside our own planet. Combine that with a high carbon composition and the right temperature, and diamond formation doesn't just happen underground. It happens everywhere. Astronomers think that as much as 1/3 of the planet's mass could be pure diamond. That's trillions of carats, more than has ever existed on Earth, mined or unmined, natural or synthetic. A literal treasure world orbiting a star far away. But don't get too excited about packing your bags and heading there with a pickaxe. 55 Cancri E is also hellishly hot. It orbits its star at a distance of just 1.5 million miles, about 25 times closer than Mercury is to our Sun. A year on this planet lasts 18 hours. It's tidally locked, meaning one side always faces the star, baking at over 2400 Kelvins, 4400 Kelvin, hot enough to melt iron, vaporize rock, and make diamond mining. A bit of a challenge. And it's not entirely peaceful either. Early observations suggested that the surface could have lava oceans, or at the very least a thin carbon-rich atmosphere venting from beneath. Recent data even shows extreme variability in its heat distribution, suggesting that something is shifting, perhaps volcanic activity or an unstable surface. This is not your grandma's jewellery box. It's more like a molten, churning planet-sized furnace that just happens to be made of gemstones. The diamond planet idea isn't based on fantasy. It comes from actual spectroscopic measurements. When scientists analysed the light coming from the 55 Cancri system, they found signs that the planet had a carbon-to-oxygen ratio far higher than Earth's. That's a big deal. Earth formed in a region of the solar system rich in oxygen, so our crust is made mostly of silicates, rock-forming compounds with oxygen and silicon. But if a planet forms in a more carbon-rich region, its interior chemistry changes entirely. Instead of granite and quartz, you get graphite, carbides, and, yes, diamond. Some models even suggest that the planet could have a crust of graphite with a thick mantle of diamond underneath. The planet may look black or metallic rather than shiny, but underneath, billions and billions of tons of crystal carbon. What's even more fascinating is that 55 Cancri may not be unique. Astronomers have already identified dozens of stars with similar carbon-rich compositions, and some of their orbiting planets could also be diamond-rich worlds. In other words, diamond planets might be more common than we thought. It's a great reminder that our concept of a normal planet, a rocky world with water and oxygen, might be a local bias. Out there in the galaxy, planets might be made of ice, lava, methane, neon, or precious gems. The universe isn't just vast, it's chemically diverse in ways that defy our imagination. This also changes how we think about planet formation. If a solar system's star has a different elemental makeup, everything about the planets changes, from core to crust to atmosphere. 55 Cancri's carbon-rich star may have seeded its planetary disk with an entirely different chemistry than ours, producing a planet that's rich not in water and silicates, but in carbon and metal, and we found it from 41 light-years away. That's the power of modern astronomy. Using nothing but light, we detected the faint signals of something as fantastical as a diamond planet, hiding in the noise of space. But here's the kicker. Even if it is made of diamond, it has no practical value to us. Why? Because value depends on rarity, and if we found a way to mine trillions of carats of diamond from a single planet, diamonds would become as common and worthless as gravel. Still, value isn't always measured in money. Sometimes it's about what something represents. A planet like 55 Cancri shows us that the universe is way weirder than we expected, that the same atoms that form beauty on Earth can, under different conditions, create an entire world of crystal carbon. A world that spins faster than Earth, bakes hotter than a furnace, and gleams with the very materials we use for engagement rings. So, yes, there really is a diamond planet out there, and it's not fiction, it's astrophysics. If you were to hover near the edge of a black hole, not fall in, just sit nearby, time itself would slow down for you. Like really slow down. To someone watching from a safe distance, it would look like you were frozen in place, barely moving, while years, centuries, even millennia ticked by for everyone else. This isn't science fiction, it's relativity, and it's completely real. Black holes are famous for being terrifying. Infinite gravity, no escape, complete darkness. But one of their weirdest effects, and maybe the most counterintuitive, is that they distort time itself. The closer you get to the event horizon, the point of no return, the more intense that effect becomes. This phenomenon is called gravitational time dilation. According to Einstein's general theory of relativity, gravity doesn't just pull on objects, it bends space and time. The stronger the gravity, the more space-time warps. And black holes have the strongest gravitational fields in the universe. To understand how time dilation works near a black hole, imagine this. Let's say you were in a spaceship, hovering just outside the event horizon of a black hole. From your point of view, everything seems fine. Your heart is beating, your watch is ticking, your ship is holding steady. But if someone were watching you from a distance, say, orbiting the same black hole a few million kilometers away, you'd appear to be moving in slow motion. Your clock would tick slower and slower the closer you got to the event horizon. From their perspective, time for you has nearly stopped. Now take that to the extreme. If you somehow stayed perfectly stationary near the event horizon for what felt like a few minutes to you, millions of years might pass for the rest of the universe. In theory, if you hovered close enough, you could time travel to the future, not by jumping through wormholes or teleporting, but just by letting time pass faster for everyone else while you experience it slowly. When you finally left the area around the black hole, you'd find a world transformed. Civilizations gone, stars moved, planets changed, while you barely aged a day. It sounds impossible, but this has been confirmed by both theory and observation. We've seen small-scale versions of this right here in our solar system. Time passes slightly slower on Earth than it does for GPS satellites in orbit. That's because gravity is weaker up there, so clocks in space tick faster. The difference is tiny, but we've measured it, and we have to account for it, or GPS would stop working. Around a black hole, those differences are huge. If you got close to a supermassive black hole, like the one at the centre of the Milky Way, Sagittarius A, the time dilation effect would be strong, but not instantly lethal. You could, in theory, orbit near it without being torn apart, depending on your distance and speed. That's the basis for scenes in movies like Interstellar, where astronauts land on a planet orbiting a black hole, and hours for them equal decades back home. That's not Hollywood exaggeration, that's actual physics. But it gets weirder. From the outside, watching someone fall into a black hole is even more surreal. As they approach the event horizon, they seem to slow down, then freeze. You'd never actually see them cross the horizon. Instead, the image would fade, redden, and eventually disappear, a result of both time dilation and gravitational redshift, where light itself is stretched and weakened by gravity. To the person falling in, though, it's instant. They pass the event horizon without noticing anything special. There's no wall at the edge, just more space, more gravity, and eventually the singularity, where time and space collapse into a single point. And that's where our understanding breaks down. We don't actually know what happens inside a black hole. Our current laws of physics can't describe it. Time and space become tangled, gravity becomes infinite, and all equations go to nonsense. It's called a gravitational singularity, a place where math just gives up. But outside, just hovering near the edge, that we understand, and we know it changes time in ways that seem almost magical. It means that in the universe, time is not constant. It can stretch, compress, and warp depending on where you are and how fast you're moving. The idea that 1 second for you might be years for someone else is not imagination. It's measurable. It's been tested using satellites, atomic clocks, and high-precision physics experiments, and black holes are just the most extreme case. Even more mind-blowing? This isn't a trick, it's not a glitch. It's how the universe works. Black holes are like windows into the deeper structure of reality, where time and space are flexible, and where gravity has more power than we ever imagined. So yes, black holes can bend light, devour stars, and crush matter. But they also do something even stranger. They mess with time. They turn clocks into illusions and make cause and effect harder to define. In a universe full of strange things, that might be one of the strangest. And it's totally real. Picture this. You scoop up just 1 teaspoon of material from a neutron star. Not a bucket, not a boulder, just a single spoonful. And it would weigh about 1 billion tons. That's not poetic exaggeration. That's the real, terrifying density of one of the most extreme objects in the known universe. To put it in perspective, 1 billion tons is roughly the mass of Mount Everest. All of it. Now imagine all that weight crammed into something the size of a sugar cube. That's neutron star material. It's so dense, it breaks our intuitive understanding of matter. So how does this happen? Neutron stars are the collapsed cores of massive stars that have gone supernova. When a star that's 8 to 20 times more massive than our sun runs out of fuel, it can no longer fight against its own gravity. It implodes, triggering a supernova explosion that ejects its outer layers into space. What's left behind is the core, now crushed down into a ball just 10 to 20 kilometers wide. That's about the size of a city, but in that tiny volume you get more mass than the entire sun. The gravity is so intense that protons and electrons are forced to combine into neutrons, hence the name neutron star. The entire thing is essentially a giant atomic nucleus. No empty space between particles, no room for molecules or atoms as we know them. It's matter in its most extreme form, squeezed into a quantum soup of neutrons, superfluids, and possibly even exotic particles like quark matter, and because the particles are so tightly packed, even the tiniest bit of it weighs an astronomical amount. You couldn't bring any of it back, of course. If you could somehow teleport a chunk of neutron star to Earth, it would instantly sink through the crust, vaporize everything around it, and likely punch a hole straight to the core. Also, you can't actually scoop neutron star material. It doesn't behave like normal stuff. The surface is a crust of super dense matter, possibly crystalline iron, just a few hundred meters thick. Beneath that, neutronium. Not a science fiction element, but a real, theoretical phase of matter made of almost entirely neutrons. And here's where things get even more bizarre. Despite their immense density, neutron stars can also spin ridiculously fast. Some rotate hundreds of times per second. We call them pulsars, firing beams of electromagnetic radiation like cosmic lighthouses. These beams are so regular that some pulsars are more accurate than the atomic clocks. The magnetic fields? Off the charts. A neutron star's magnetic field can be 1 trillion times stronger than Earth's, and in rare cases, magnetas, they're even stronger. These fields are so powerful they can distort atoms, tear apart electronics, and even affect the chemical bonds in your body from thousands of kilometers away. And yet, these stars are invisible to the naked eye. They hide in the darkness, detectable only through X-rays, gamma rays, and radio signals. You could pass one and never see it until it was far too late. So yes, 1 teaspoon of neutron star material weighs more than the tallest mountain on Earth. It's a reminder of how deceptive scale can be in space. Something small can be impossibly massive. Something invisible can bend the laws of physics, and something born in the death of a star can be one of the most extreme objects in the universe. Welcome to HD 1897733b, a planet where weather takes a violent, unforgiving turn. From a distance, it looks peaceful, a rich blue hue that makes it resemble Earth. But don't be fooled. That inviting colour, it's the result of silicate particles in its atmosphere, the same stuff used to make glass. But this planet doesn't just have glass in the air, it rains it, and not just gently. The wind speeds on HD 18973b reach up to 8,700 kilometers per hour, nearly 7 times the speed of sound. That means when the glass rain falls, it gets blasted sideways through the atmosphere like tiny, razor-sharp bullets. Imagine being caught in that storm. It's not a place you'd want to stand, even in the best protective suit. The atmosphere alone would rip it to shreds, before the glass had a chance to slice anything. HD 89733b is a hot Jupiter, a class of gas giant exoplanets that orbit extremely close to their stars. It's about 64 light-years away, and it orbits its star at just 4.7 million kilometers. That's more than 10 times closer than Mercury is to the Sun. The result? An environment so hot and turbulent that it redefines the word hostile. Temperatures climb to over 1,000 degrees and 800 wind on the dayside. The heat is intense enough to vaporize rock, creating clouds of molten silicate particles. These clouds condense high up in the atmosphere, then fall back down as molten glass. But thanks to those incredible winds, the rain doesn't fall vertically. It's launched sideways in giant, searing horizontal arcs across the sky. This isn't science fiction. These features have been directly observed using the Hubble Space Telescope and Spitzer Infrared Space Telescope. By studying the planet's light spectrum as it passes in front of and behind its star, scientists can infer not just the temperature, but the chemical composition and motion of its atmosphere. The blue colour itself is misleading. On Earth, our sky is blue because of Rayleigh scattering, sunlight bouncing off nitrogen and oxygen. On HD 18973b, that blue is caused by light scattering off tiny glass particles floating freely in the air. It looks beautiful, but that shimmer is coming from microscopic shards. The wind on this world is so intense because of its tidal locking. One side always faces the star, and the other is plunged into perpetual night. This causes extreme temperature gradients across the surface, driving monstrous jet streams around the planet at unimaginable speeds. We think of Earth storms as chaotic, but they're nothing compared to the weather systems on HD 189733b. This isn't just a rough forecast. It's a global storm system made of fire, wind and glass, circling endlessly with no seasons, no calm, no pause. HD 189733b was one of the first exoplanets where weather conditions were actually mapped. That alone makes it scientifically important, not just for how bizarre it is, but for what it tells us. If we can detect sideways glass rain on a planet 64 light-years away, what else can we find? And what does this tell us about the range of climates planets can have? It turns out, Earth-like is just one small flavour of what's possible. This planet serves as a stark reminder. When we look out into the galaxy, we shouldn't expect to find comfort zones. Many worlds don't gently rotate under sunny skies. They howl, burn and cut through anything that enters their atmosphere. And some do it while glowing blue, wearing a disguise that hides just how brutal they really are. It's one of the strangest puzzles in modern astrophysics, a contradiction that seems impossible, yet refuses to go away. We've discovered stars that, according to our best measurements, appear to be older than the universe itself. And yes, that should be impossible. The universe, based on precise measurements from the cosmic microwave background, is about 13.8 billion years old. That's the age we get from mapping the Big Bang's leftover radiation, calculating how galaxies move, and observing the oldest light we can see. It's a number cosmologists are extremely confident in. So how then did we end up with a star like HD 1823, also known as the Methuselah star, which for a long time was estimated to be around 14.5 billion years old? That would make it 700 million years older than the universe. And unless our entire understanding of time and space is wrong, something here clearly doesn't add up. HD 140283 is located about 200 light-years away, in the constellation Libra. It's an old, metal-poor subgiant, one of the most ancient stars known. Its low metallicity, meaning very few elements heavier than helium, suggests it formed at a time when the universe was still fresh from the Big Bang, before stars had produced and distributed heavier elements. In fact, it's so ancient it likely belongs to the second generation of stars ever formed. Its age was calculated using stellar evolution models, which look at a star's brightness, temperature, and chemical makeup to estimate how long it's been burning. But when the number came out older than the universe itself, it caused a stir, a big one. The most likely explanation is not that HD 140283 defies cosmic history, but that there's uncertainty in our measurements. The universe's age isn't measured to the exact second, and neither is the stars. When you account for margins of error in both distance and stellar models, the ages could align more comfortably. In fact, updated data from the Gaia Space Observatory, which refines star distances with extreme precision, has revised the Methuselah star's age downward, placing it closer to 13.2 billion years. That brings it just under the age of the universe, solving the contradiction, at least for now. Still, the margin is slim, and HD 140283 isn't alone. A handful of other ancient stars like SMSS J031300, 36, 6C7083 and 3 have popped up with similarly confounding age estimates. Each time it forces astronomers to go back, recheck models and sharpen their instruments. These stars become cosmic truth tests, pushing the boundaries of what we know about time, physics and star formation. More broadly, this raises important questions. How quickly did the first stars form after the Big Bang? Could some stars have formed sooner than we expected before galaxies even took shape? Are there unknown factors that make certain stars appear older than they really are? These puzzles are more than quirks. They're stress tests for our cosmology. Every time we find a star that doesn't fit, it's a chance to uncover something deeper, maybe a missing piece in stellar evolution, or even a hint that our model of the universe's expansion still has gaps. Methuselah stars serve another role too. They help anchor the timeline of cosmic history. If a star is nearly as old as the universe, it means it formed very soon after the Big Bang, giving us insights into how fast the first stars appeared, how early galaxies began assembling, and what the chemical landscape of the early cosmos looked like. It's a reminder that even after 13.8 billion years, the universe can still throw us a curveball. So while no star is likely literally older than time itself, some are so close to the beginning of everything that they feel like artifacts from another epoch, witnesses to the dawn of light still burning. It doesn't matter if you're running marathons, eating kale, or getting 10 hours of sleep. If you want to age just a tiny bit slower, your best bet is to move to sea level. Because thanks to the bizarre physics of gravity and time, the lower you are in Earth's gravitational field, the slower time passes for you. This isn't metaphor or theory. This is a measurable, proven fact. According to Einstein's theory of general relativity, time is affected by gravity. The stronger the gravitational field, the more time slows down. This phenomenon is called gravitational time dilation, and it's not just something that happens near black holes or in deep space. It's happening to you, right now, on Earth. If you were to live at the bottom of a valley for your entire life while your twin sibling lived on a mountaintop, they would, very slightly, be older than you by the end of your lives. Not because of lifestyle or environment, but because time literally moved faster for them. Your clocks would tick at slightly different speeds, even if synchronized perfectly at birth. How much faster? Not by much. The difference is measured in nanoseconds, billionths of a second, over the course of a year. But the effect is real and has been measured by atomic clocks in laboratories and on satellites. In fact, the experiment was done in 2010, using two super precise atomic clocks, one kept a few feet higher than the other. After some time, the elevated clock had ticked slightly ahead. It's a tiny effect, but not trivial, especially when you're dealing with precision systems like GPS. The satellites that power GPS signals orbit about 20,000 kilometers above Earth. Because they're farther from Earth's gravity, time passes faster for them than it does on the surface. This means engineers must correct for relativity, adjusting the clocks so they match Earth time. Without these corrections, GPS devices would drift by kilometers per day, making the system unusable. Time, it turns out, is not a universal constant. It depends on where you are and how fast you're moving. That's not just strange, it's a direct challenge to the everyday assumption that clocks always tick evenly, everywhere. The effect isn't limited to altitude either. Speed also affects time. According to special relativity, the faster you move, the slower your time passes relative to someone at rest. That's why astronauts on the International Space Station, who orbit Earth at about 28,000 kilometers each, actually age a little slower than people on the ground. Combine that with the weaker gravity at orbital altitude, and the time shift is a delicate balance of both effects. In the case of Earth's surface, gravitational time dilation dominates. The deeper you are in a gravity well, like Earth's, the more space-time is curved, and the more time slows down. This means the centre of Earth experiences time more slowly than the surface. So theoretically, your feet age slower than your head. The difference is so minuscule it's functionally meaningless, but it's real. And yes, if you want to take this to the extreme, it means someone living in the basement is technically younger than someone living in a penthouse, though only by a fraction of a nanosecond. These relativistic effects become dramatically more noticeable in extreme environments. Near a black hole, time can slow down so much that a minute for you might be years for someone else. as we saw in Interstellar. But even here, on this planet, the effects are playing out in the background, quietly nudging our clocks and calendars ever so slightly. And there's something poetic about that. We tend to think of time as rigid, as absolute. But the universe says otherwise. Your location and motion shape the rate at which you move through time. It's not some mystical idea. It's built into the very geometry of space-time. So if you want to slow down aging, not metaphorically but physically, don't buy fancy creams. Just move closer to the centre of Earth. It won't add years, but it will, technically, add time. Supernovae are often treated as the ultimate cosmic fireworks, stars exploding with such violence they outshine entire galaxies for weeks. But even supernovae have limits. If you want to witness the most energetic explosions the universe can produce, you have to go bigger. You need a gamma-ray burst, or GRB. Gamma-ray bursts are brief, terrifying flashes of high-energy radiation. They don't last long, usually a few seconds to a couple of minutes, but in that short window, they release more energy than our sun will emit over its entire 10 billion year lifetime. Let that sink in. In less than a minute, a GRB can outshine everything in the observable universe, all at once, from a single point in space. These explosions are so powerful they can be detected from billions of light years away, across most of the visible universe. Some of the ones we've observed likely happened not long after the Big Bang. Their light has travelled for over 13 billion years just to reach us. So what causes something this extreme? There are two main types of GRBs. Long-duration GRBs, lasting more than 2 seconds, are typically caused by the collapse of a massive star, even bigger than the ones that create regular supernovae. These stars don't just blow up, they collapse into black holes, and in the process they eject focused beams of gamma rays at nearly the speed of light. If one of those beams is pointed directly at Earth, we see a burst. Short-duration GRBs under 2 seconds come from the merging of 2 neutron stars or a neutron star and a black hole. These collisions are cataclysmic, producing a flash of energy so intense it can rip apart nearby space-time. Either way, what we're seeing is raw, uncontrolled violence at a cosmic scale, the universe unhinged. One of the most powerful gamma-ray bursts ever recorded happened on October 9th, 2022. It was named GRB 20109A, but astronomers dubbed it the Boat, short for brightest of all time. It was so luminous that it blinded many gamma-ray instruments and even had effects on Earth's atmosphere. The burst lasted several minutes, and despite being 2.4 billion light-years away, it was so powerful it could be studied across a wide range of wavelengths. For context, that would be like someone lighting a match on the moon and having it melt your sunglasses on Earth. What's even more unsettling is what happens if a gamma-ray burst hits a planet directly. If a GRB beam struck Earth from close enough, say within a few thousand light-years, it could strip away the ozone layer, expose the surface to deadly radiation, collapse ecosystems, and potentially trigger a mass extinction. There's a theory that one of Earth's past extinction events may have been triggered by a nearby GRB. We'll never know for sure, but the possibility is very real. The good news? GRBs are narrow beam events. They're like sniper shots, not bombs. Unless a beam is aimed exactly at us, we're safe. And statistically, they're rare in galaxies like ours. Still, the idea that a planet-killing ray could streak across the galaxy at light speed, with no warning, is one of the more chilling realities of space. But GRBs are also tools. They allow scientists to study star formation in the early universe, explore the deaths of the most massive stars, and learn more about black hole birth. Because their light travels so far, they act like cosmic lighthouses, illuminating the ancient universe. In fact, GRBs are some of the only objects that let us see back to the cosmic dark ages, just a few 100 million years after the Big Bang, before galaxies fully formed. They're violent, deadly, and completely indifferent to life. But they're also one of the few keys we have to unlock in the universe's deepest history. So no, the most powerful explosions aren't supernovae. Those are loud, yes, but gamma-ray bursts are something else entirely. Fast, focused, and devastating beyond comprehension. We tend to think we have a pretty solid grasp on reality. We've mapped the stars, landed probes on distant worlds, measured the age of the universe. But for all that achievement, we've run into one enormous problem. Most of the universe is completely invisible, and worse, we don't even know what it is. Let's break this down. Everything we can see, stars, planets, galaxies, nebulae, people, trees, dust, all of it, every speck of matter ever observed by humans, accounts for just about 5% of the total mass energy content of the universe. 5%. The remaining 95%, that's made of two things, dark matter and dark energy. Both are invisible, both are mysterious, and both dominate the structure and behaviour of the entire cosmos. Let's start with dark matter. Back in the 1930s, astronomers noticed something strange. Galaxies were rotating too fast. The stars near the edges of galaxies weren't slowing down the way Newtonian physics said they should. It was as if there was something invisible holding them together, some unseen mass providing extra gravity. Later, observations of galaxy clusters and gravitational lensing, where light from distant objects gets bent by invisible mass, confirmed it. There's a lot more mass in the universe than we can account for. Roughly 27% of the universe is made of this stuff. We call it dark matter. What is it? We don't know. It doesn't emit or absorb light. It doesn't interact with normal matter in any meaningful way, except through gravity. Some think it could be made of undiscovered particles, WIMPs, axions, or sterile neutrinos. Others think we may need to revise gravity itself. But despite decades of research, dark matter remains a ghost, detectable only by its gravitational pull. And then there's dark energy, even weirder. In the late 1990s, two independent teams of scientists were studying distant supernovae to figure out how fast the universe's expansion was slowing down. Except, it wasn't slowing down. It was speeding up. Some unseen force was pushing galaxies apart, accelerating the expansion of space itself. This force, whatever it is, makes up about 68% of the universe. We call it dark energy. It's not like energy from the sun or your car battery. It seems to be an intrinsic property of space, tied to the fabric of the cosmos in ways we don't yet understand. Its discovery earned the 2011 Nobel Prize in Physics and opened a massive can of existential worms. Dark energy is why the universe will likely keep expanding forever. It may even lead to a future scenario called the Big Rip, where the expansion becomes so violent it tears galaxies, stars, and atoms apart. That's still speculative, but it shows how little we understand the rules running the show. Let's recap. All the light, matter, and energy we can detect, every galaxy we've ever photographed, every molecule we've ever measured, is just a cosmic rounding error. The vast majority of the universe is dark, untouchable, and possibly undetectable by conventional means. Think about that. The stuff we call reality is sitting on a tiny island in a vast ocean of mystery. And this isn't fringe science. It's the standard model of cosmology. It's what physicists teach, what satellites like Planck, WMAP, and Euclid are built to study. It's the reason particle colliders keep smashing atoms together. We're trying to get a glimpse of what's really out there. We're used to thinking of science as having answers, but sometimes it reminds us of how little we know. The universe is 95% missing, and we're still fumbling in the dark trying to explain why. Not with superstition, with data, with equations, with telescopes so sensitive they can see the echoes of the Big Bang. And still, they tell us, you're barely scratching the surface. When we look up at the night sky, it feels peaceful. Stars twinkle quietly. The Milky Way arches gently across the horizon. It's easy to think of the universe as calm and unchanging, but on the grand scale of galaxies, space is anything but still. Galaxies are constantly in motion, hurtling through the universe at hundreds of thousands of kilometers per hour, drawn toward one another by gravity. And sometimes they crash. Not just a close pass or a glancing brush, full-on collisions between galactic titans. And we're next. The Milky Way galaxy, the one you're living in right now, is on a direct course for a head-on collision with our neighbour, the Andromeda Galaxy. It's not a question of if, it's a question of when. Andromeda is currently about 2.5 million light-years away, but it's moving toward us at about 110 kilometers per second. That's over 390,000 kilometers km/h. At that rate, the two galaxies will collide in about 4 billion years. You might expect the result to be utter destruction. Stars smashing into each other, solar systems vaporized, black holes going wild. But here's the twist. Despite the chaos, very few stars will actually collide. That's because galaxies are made mostly of empty space. The distance between stars is vast compared to their sizes. So when galaxies merge, stars tend to pass by each other, not crash. Instead, the real drama happens on a much larger scale. The gravitational pull between the galaxies distorts their shapes, flinging stars into new orbits, warping spiral arms into long trailing tails. Over time, both galaxies will be stretched, twisted, and eventually combined into a new, single structure. Astronomers call this future product Milkomeda, or Milkdromeda, a giant elliptical galaxy that will replace both the Milky Way and Andromeda. During the collision, both central supermassive black holes, one in each galaxy, will spiral toward each other and eventually merge in a titanic event that could send gravitational waves rippling across the cosmos. So what happens to Earth? Assuming it survives the Sun's future red giant phase, which itself will likely engulf the inner planets, Earth will still be around for the galactic merger. From the surface, the night sky will transform. Andromeda will grow larger and brighter for millions of years, eventually dominating the sky with a stunning view of twisted stars and colliding structures. It'll be one of the most spectacular celestial events imaginable. Though any humans still around will have long since become a different kind of civilization, the Milky Way won't be the same cozy spiral it is now. Everything will be reshaped, and it's not just us. Galactic collisions are common. In fact, many galaxies we observe with telescopes are either in the process of merging or show signs of past collisions. These events are a normal part of galaxy evolution. Collisions trigger starbursts, collapse gas clouds, and help galaxies grow in size and complexity. That means the beautiful spiral structure of the Milky Way, temporary. Spiral galaxies often evolve into elliptical galaxies after enough collisions. Over billions of years, that's how the universe slowly transitions, from young, energetic spirals to older, puffier, more spherical galaxies. So yes, the Milky Way is headed for a crash, but not in a fiery explosion of chaos. Instead, it'll be a gravitational ballet spanning millions of years, slowly blending two giant galaxies into one. It's not something to fear. It's part of the life cycle of galaxies, an inevitable next chapter in our cosmic story. And the best part? We've already started observing similar galactic mergers all across the universe. When we look at distant galaxies, we're seeing versions of our own future, cosmic previews of what's to come. The sky looks still, but the universe is always moving, and one day, the Milky Way will never look the same again. Planets, as we understand them, orbit stars. That's just how it works. Earth orbits the Sun, Jupiter orbits farther out, and every other planet we've ever known follows that rule. But nature, as it turns out, doesn't always follow our expectations. Because out there, in the darkness between stars, are planets that don't orbit anything. They're called rogue planets, lonely, free-floating worlds drifting endlessly through interstellar space, and we've actually found some. One of the most famous is PSO J3 18.5-22, discovered in 2013. It's located about 80 light-years from Earth, and it has no host star. It's just wandering, completely alone, with no sun to orbit and no light to call home. It's massive, about 6 times the size of Jupiter, and likely formed in a star system before being flung out by gravitational interactions. These planets are not rare. In fact, some estimates suggest that rogue planets may outnumber stars in our galaxy. That's right. There could be billions of these dark, starless worlds drifting silently through the cosmos. How do planets end up like this? There are 2 main possibilities. First, they may form inside a planetary system like ours, but during the chaotic early stages of formation, they get gravitationally kicked out. Maybe 2 massive planets pass too close to each other, and one gets launched into deep space. Or maybe a nearby star disrupts the system during a close pass. Either way, the planet is ejected, and once it's out, there's no pulling it back in. The second possibility is even more intriguing. Some rogue planets might have formed alone, outside of any star system. This idea challenges our standard models of planetary formation, which depend on the presence of a central star. But if gas and dust can collapse into a planet without ever igniting into a star, then rogue planets might be born directly from stellar leftovers, scattered through galactic space. What would it be like on one of these worlds? Cold. Very cold. With no star to provide heat, a rogue planet's surface temperature could drop to hundreds of degrees below zero, especially if it's far from any radiant energy sources. It would be cloaked in perpetual darkness, with no sunrise, no seasons, no orbit, just endless night. And yet, that doesn't necessarily mean they're lifeless. Some scientists speculate that large rogue planets, especially gas giants, could retain internal heat for billions of years. If they have thick atmospheres, they might trap that heat, keeping subsurface oceans or deep atmospheric layers relatively warm. In theory, microbial life could exist on a rogue planet sustained by geothermal energy rather than sunlight. That idea forms the basis of some science fiction too. Self-sustaining biospheres deep underground, hidden from view, clinging to life in the void. It sounds fantastical, but it's grounded in physics. Detecting these planets is difficult. They emit almost no light, and don't have the telltale wobble or transit patterns we use to detect exoplanets around stars. We usually spot them through infrared imaging, where the residual heat of the planet glows faintly. Future telescopes, like the Nancy Grace Roman Space Telescope, could help identify thousands more, possibly even smaller ones the size of Earth. The existence of rogue planets changes how we think about what a planet even is. We tend to define them by their relationship to stars or sand, but these worlds break that rule. They roam freely, unbound by the orbits we take for granted. It's a reminder that the universe is not built to satisfy human categories. It's more creative, more chaotic, and sometimes more lonely than we expected. Somewhere out there, in the darkness between stars, a world spins alone, unseen, unanchored, and very, very real. Black holes have a reputation for being mysterious, destructive, and inescapable. But the strangest thing about them isn't what they destroy, it's what they do to reality itself. At the heart of a black hole, time doesn't just slow down. It doesn't just stretch, it stops. And space, the three-dimensional world we move through, gets so warped that inward becomes outward, and forward in time becomes a direction in space. It's not a metaphor, it's what Einstein's equations literally predict. Let's start at the edge, the event horizon. This is the boundary around a black hole where gravity becomes so strong that nothing, not even light, can escape. From the outside, it looks like a surface. But it's not a solid wall. It's a point of no return. Once you cross it, you're going in. Always. Now imagine falling in. As you approach the event horizon, an outside observer would see you slow down. You'd appear to freeze at the edge, your image fading and redshifting until it disappears. From your perspective, though, nothing unusual happens. You pass through the horizon without feeling a thing, assuming the black hole is big enough that tidal forces aren't tearing you apart just yet. But then things start to get weird. Once you're inside the event horizon, the rules change. In fact, the dimensions themselves start to switch roles. What was once space, the directions you could move, becomes time. And what was time becomes something more like space. In simple terms, moving forward in time now means moving inward toward the singularity. You can't stop it. Just like you can't stop aging or pause time in the real world, inside a black hole, you can't stop falling inward. It's not just where you're going, it's when you're going. And the center? That's the singularity, a point of infinite density and zero volume, where all of the black hole's mass is concentrated. Physics breaks down here. Gravity becomes infinite. Our current models, general relativity, quantum mechanics, stop working. The equations just explode into nonsense. Time, at the singularity, ceases to exist as a meaningful concept. There is no after the singularity. There's no ticking clock, no next second. It's not even that time moves slowly, it simply doesn't move at all. There's no time to pass through, just an end. But here's what might be the most mind-bending part. If space and time switch roles, then inside a black hole you can't move outward in space any more than you can move backward in time. Escaping a black hole is as impossible as going back in time, because they're now functionally the same thing. It's like living in a world where all roads lead to the same destination, and no matter how you try to turn, you always end up going forward in time, which now means plunging deeper into gravity. The deeper you fall, the less the concept of outside even makes sense. This is why black holes are so much more than just dense objects. They're geometric anomalies. They tear holes in the fabric of space-time, creating regions where the laws of reality get rewritten. They are natural laboratories for extreme physics, where ideas like causality, entropy, and even information itself get challenged. Physicists are still grappling with what happens inside. Some theories suggest that the singularity is not truly a point, but something quantum, perhaps a fuzzy structure, or even a bridge to another universe, a wormhole maybe. Others propose that information falling into a black hole is somehow stored in the event horizon itself, giving rise to the holographic principle. No one knows for sure. The math gets us close, but the truth remains hidden behind the event horizon. It's like a locked vault of physics, one we may never open directly. But here's what we do know. In a black hole, space folds in, time winds down, and everything we thought was separate, past and future, inside and out, motion and stasis, begins to blur. You may not feel it, but right now the entire Milky Way galaxy, along with everything in it, including you, is moving at a staggering 600 kilometers per second in one specific direction through the universe. Not because we're drifting aimlessly, but because something enormous is pulling us. Something we can't see. Something known ominously as the Great Attractor. The name sounds like a sci-fi villain, but it's real. Discovered in the 1980s, the Great Attractor refers to a mysterious gravitational anomaly, a region of space located roughly 150 to 250 million light-years away, in the direction of the constellations Norma and Centaurus. Astronomers noticed that dozens of galaxy clusters, including our own local group, are moving toward that point, all drawn by an unseen force. And we're not just moving slightly. The entire Laniakea supercluster, which contains over 100,000 galaxies, is drifting toward the Great Attractor at a velocity that defies random motion. But here's the weird part. We can't see what's causing it. The Great Attractor lies behind the zone of avoidance, a dense band of stars, gas and dust at the centre of the Milky Way that blocks our view. Optical telescopes can't penetrate it. It's like trying to look through a glowing fog with sunglasses on. Whatever lies beyond that curtain is hidden. So how do we know something is there? astronomers mapped galaxy movements across vast regions of space and noticed that velocities didn't make sense. Galaxies were accelerating in one direction, toward the zone of avoidance, as if something was pulling on them. The gravitational influence needed to explain this drift would require something with hundreds of thousands of times the mass of the Milky Way. Some of that mass has been partially identified. Observations using infrared and X-ray telescopes have revealed galaxy clusters like the Norma cluster, which sits at the heart of the Great Attractor's suspected location. But the full picture remains unclear. Even today, the exact composition of the Great Attractor is unknown. Is it just a particularly massive supercluster of galaxies? Is there a hidden concentration of dark matter? Or are we being pulled towards something even larger? It gets stranger. Further studies reveal that even the Great Attractor may be just a local feature in an even grander flow. There's another gravitational anomaly beyond it, even farther away, called the Shapley supercluster, an enormous mass of galaxies and dark matter that may be influencing the movement of entire regions of the universe. It's like a cosmic tug of war, and we're caught in the ropes, moving towards something vast, ancient, and mostly invisible. This flow of galaxies is sometimes referred to as the dark flow, though that term is debated. Still, the basic idea is clear. On scales of hundreds of millions of light years, galaxies aren't just passively expanding away from each other. Some are being pulled, coherently, across the universe, as if drawn toward gravitational wells we can barely detect. What this tells us is both thrilling and unsettling. There are structures in the universe larger than we can see, shaping the motion of entire galaxies, and some of them are still hidden behind our own Milky Way, locked behind a wall of light and gas. The Great Attractor is a reminder that cosmic motion isn't random. Galaxies move for reasons. They drift, fall, and collide because of forces we're only beginning to map. And sometimes the source of those forces is completely invisible. Something massive is pulling us across space, and we don't fully know what it is, but it's there. If there's one rule you've probably heard about the universe, it's this: nothing can travel faster than the speed of light. It's one of the bedrock principles of modern physics, a cosmic speed limit built into the structure of space-time itself. And yet, in the early universe, something did move faster than light. Not matter, not energy, space itself. In the first fraction of a second after the Big Bang, specifically from about 1036 to 1032 seconds, the universe underwent a period of exponential expansion called cosmic inflation. During this brief, almost incomprehensibly short window, space didn't just expand, it exploded outward at speeds that far exceeded the speed of light. And yes, that's allowed. Because while nothing can move through space faster than light, the expansion of space itself isn't bound by that rule. General relativity allows space-time to stretch as quickly as it wants, even faster than light, because it's not a particle moving within the universe, it is the universe. This concept is one of the most counterintuitive, yet most important ideas in cosmology. Without inflation, we can't explain why the universe looks the way it does today. Here's the problem inflation solved. When we look at opposite ends of the observable universe, say two galaxies separated by 90 billion light-years, they appear almost identical in temperature and density, but according to pre-inflation models, there's no way those regions could have ever communicated. Light simply didn't have enough time to travel between them. So how did they end up so similar? That's called the horizon problem. Inflation solves it by proposing that before this rapid expansion, the universe was much smaller, small enough for all parts to interact and reach equilibrium. Then inflation kicked in, blowing the entire thing up faster than light, preserving that uniformity across vast cosmic distances. It also explains the flatness problem, the mystery of why the universe appears geometrically flat, not curved like a sphere or a saddle. Inflation stretched any initial curvature so wide that, from our vantage point, the cosmos now looks perfectly flat. So how fast did inflation occur? We're talking about space doubling in size every 1035 seconds, over and over again. In just a tiny sliver of a second, the universe expanded by a factor of at least 1026. That's like taking a subatomic particle and making it bigger than the entire observable universe in less than the blink of an eye. After that burst, inflation stopped. The expansion slowed down, and matter and radiation took over, eventually forming atoms, stars and galaxies. But the fingerprints of inflation are still visible, etched into the cosmic microwave background, the faint afterglow of the Big Bang. Slight fluctuations in temperature and density seen in this background match exactly what inflation theory predicts. We've even used satellites like WMAP and Planck to study those tiny fluctuations. They give us a map of the early universe, a snapshot of its structure less than 400,000 years after birth. And it's because of inflation that that map makes sense. So yes, space once expanded faster than the speed of light. And no, that doesn't break physics. It actually holds it together. It reminds us that the rules we experience as speed limits, distance, even the flow of time, are part of a larger framework. A framework that can, under the right conditions, stretch, flex, and explode in ways our everyday experience can't begin to prepare us for. The universe, in its infancy, was fast, wild, and infinitely strange. And somehow, out of that chaos, came everything. It sounds like a line from a poem or a stoner's midnight thought experiment. There are more stars in the universe than grains of sand on Earth. But this one isn't just poetic, it's scientifically true. And once you do the math, it becomes one of the most awe-inducing, brain-stretching facts about the cosmos. Let's start with the sand. Estimating the number of grains of sand on Earth is tricky, but scientists have actually taken a swing at it. If you count every beach, desert, seabed, and sandbox, and assume an average grain of sand is about 0.5 millimeter wide, the total number of grains comes out to around 7.5 Voro 1018. That's 7.5 quintillion grains of sand. A 7 followed by 18 zeros. That's a lot of sand. But now look up. There are estimated to be over 100 billion galaxies in the observable universe. Some estimates go even higher, but let's be conservative for now. Each of those galaxies contains 100 billion to 1 trillion stars. That means the total number of stars out there is somewhere in the neighbourhood of 1022 to 1024. That's 10,000 times more stars than grains of sand. And we're just talking about the observable universe, the part we can see based on the speed of light in the age of the cosmos. The actual universe may be much larger, potentially infinite. If that's the case, the number of stars is also potentially infinite. Now pause and really think about that. Every grain of sand you've ever touched, at the beach, in your shoe, between your fingers, represents thousands of stars, entire galaxies of suns, many with their own planets, their own systems, maybe even their own versions of life. And that's just one grain. It shifts your sense of scale. We often picture the night sky as sparse, a few bright stars scattered across a black canvas. But that's an illusion of distance. In reality, the universe is packed, bursting with stars. We just can't see most of them because they're too far, too faint, or drowned out by light pollution. But they're there. Let's make it even more vivid. In a single teaspoon of sand, you might have tens of thousands of grains. Imagine a corresponding number of solar systems, not just stars but potential worlds, with gas giants, rocky exoplanets, moons, oceans, storms, atmospheres. In recent years, we've confirmed that most stars do have planets. Many have multiple. That means we're not just talking about a universe full of stars. We're talking about a universe full of worlds. Billions upon billions of planets. Trillions, maybe. The more we study the cosmos, the more this number grows. We've now discovered thousands of exoplanets, and those are just the ones close enough to detect with current technology. The true number is vastly higher, and yet here we are, on a pale blue dot, orbiting an ordinary star in a fairly quiet corner of a galaxy that's one of hundreds of billions. It's easy to feel small in all this. And maybe that's the point, but it's also a kind of invitation. If there are more stars than grains of sand, then the odds of something else being out there, some other form of life, some other intelligence, some other place with oceans and skies and stories, start to feel less like science fiction and more like probability. So the next time you're standing on a beach, let some sand run through your fingers, and remember, for every grain, there are thousands of stars, millions of planets, a whole universe humming in silence just above your head. When you look at Saturn, those iconic rings feel timeless, like they've always been there, orbiting that pale yellow giant for billions of years. But here's the twist. They're not ancient. In fact, Saturn's rings might be younger than the dinosaurs. For most of modern astronomy, the assumption was that Saturn's rings formed along with the planet itself, roughly 4.5 billion years ago, back in the chaotic youth of the solar system. It made sense. Big planet, big ring system, old age. But newer data paints a very different picture. Saturn's rings may have formed just 100 to 200 million years ago, meaning they didn't exist during the Mesozoic era. When Tyrannosaurus rex roamed the Earth, Saturn may have been a ringless giant, looking completely different from the version we know today. So, what changed? The clue comes from the rings themselves. They're made mostly of water ice, clean, bright, and surprisingly pure. Over billions of years, cosmic dust and micrometeoroids should have dirtied them, darkening their shine, but they're still pristine, almost too pristine. This implies they're relatively young. They haven't had enough time to collect much cosmic grime. That's where NASA's Cassini mission comes in. From 2004 to 2017, Cassini orbited Saturn, delivering the most detailed images and measurements ever taken of the planet and its rings. During its final orbits, a daring series of dives between the rings and the planet itself, it gathered precise data on the rings' mass and composition. The results were striking. The rings were less massive than expected, meaning they couldn't have survived the gravitational chaos and collisions of billions of years. They're fragile, too fragile to have endured the full lifespan of the solar system. So how did they get there? One leading theory is that a comet or icy moon, perhaps something the size of Mimas or Enceladus, wandered too close to Saturn and was ripped apart by tidal forces. This is called crossing the Roche limit, the point where a planet's gravity can overcome an object's self-gravity and pull it apart. The shattered debris then spread into orbit, forming the majestic rings we see today. Over time, collisions between ice chunks smoothed the system into the elegant flat disks we know. Another possibility is that multiple small moons collided, perhaps nudged out of alignment by gravitational tugs from Saturn's larger moons, or interactions with orbital resonances. Either way, the evidence suggests Saturn's rings are not relics from the birth of the solar system. They're a recent addition. They formed long after Earth stabilized, long after life crawled from oceans, and well after the first forest took root, and they might not last. The same Cassini data that showed the rings' youth also revealed something ominous. They're slowly disappearing. Particles from the rings are spiraling inward, pulled by Saturn's gravity in a process called ring rain. In perhaps another 100 million years, the rings may be gone entirely, absorbed into Saturn's atmosphere or falling into the planet itself. So we're living in a cosmic moment, a rare window in time when Saturn just happens to be wearing a spectacular set of icy jewellery. In the long history of the solar system and its long future, that window is brief. If we'd evolved a few 100 million years earlier or later, we might not have known Saturn's rings ever existed. They are beautiful, they are temporary, and they are younger than the last dinosaur. When we look up at the moon, it feels close. You can see its craters with a decent pair of binoculars. Astronauts have been there and back in less than 2 weeks. It's our cosmic next-door neighbour, close enough to inspire ancient myths, far enough to remain untouchable for most of history. But here's the jaw-dropper. You could fit all 7 other planets of the solar system – Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune – side by side in the space between Earth and the Moon. And you'd still have room to spare. That sounds impossible, right? The Moon feels close, but the planets are huge. How can you cram Jupiter and Saturn into that space and not run out of room? Let's run the numbers. The average distance from Earth to the Moon is about 384,400 kilometres. That's not the edge of our atmosphere, not even close. It's nearly 30 Earths away. Now line up the diameters of the planets. Mercury, 4,779 km Venus, 12,004 km Mars, 6,779 km Jupiter, 130 ounces more than 20 Saturn, 116,460 km Uranus, 50th tons 24 km Neptune, 40 ounces 2,400 km. Add them all up, 4879, 12 on 2 4 679, 1 20 116,460 joules, 5724, 40 ounces 2 4 379 is 10 km. That's 5,000 km less than the Earth-Moon distance. Which means, in theory, you could line up every planet in our solar system side by side in a neat row between Earth and the Moon, and still have a little breathing room. No stacking, no bending the rules. Just a literal lineup of planets, floating in the same space the Moon currently occupies in the night sky. Now obviously this isn't suggesting that would ever happen. The gravitational chaos of that arrangement would shred Earth, the Moon, and the planets themselves. Jupiter alone could unbalance our entire orbit. But that's not the point. The point is scale. We think of space as distant, massive, unreachable, and it is in a lot of ways. But sometimes what's truly surprising isn't how big things are. It's how much empty space there is between them. The Moon feels close, but the gap between Earth and the Moon is staggering by human standards. It's so big that it could accommodate every other planet we've ever studied and still leave a gap wider than Earth's diameter. There's a haunting photo taken by NASA's OSIRIS-REx spacecraft of Earth and the Moon in the same frame. 2 tiny orbs suspended in a vast sea of black. And what's striking isn't just how small they look, it's how far apart they are. That photo captures what 384,400 kilometres of distance actually looks like in open space. So the next time you look at the Moon and think, that doesn't seem too far, remember? You're looking across a gap large enough to contain the entire planetary lineup of the solar system. And that's just one step away. The solar system isn't just vast, it's sparsely packed, full of emptiness so immense it can hold worlds between worlds, silently, invisibly, every night above your head. It seems like a no-brainer. Mercury is the closest planet to the Sun, so it must be the hottest, right? Nope. That honour goes to Venus, the second planet from the Sun, and its surface is so scorching it could melt lead. Venus is, on average, about 108 million kilometres from the Sun. Mercury is closer, only about 58 million kilometres away. But Venus consistently wins the temperature contest. Its average surface temperature is around 464 degrees, 860 Celsius, hotter than any other planet in the solar system, including Mercury. And the reason why? Venus has an atmosphere, but not just any atmosphere. Venus's atmosphere is a choking, crushing, heat-trapping blanket made up of 96.5% carbon dioxide, with clouds of sulfuric acid and trace elements of nitrogen. It's dense, about 90 times heavier than Earth's atmosphere at sea level. Standing on the surface of Venus would be like standing 900 metres underwater on Earth. That thick atmosphere acts like a thermal prison. Here's how it works. Sunlight enters the atmosphere and heats the planet's surface. But instead of letting the heat radiate back into space, as Earth's thinner atmosphere does, Venus's dense CO2 keeps it trapped. The heat bounces around, building up over time in a process called runaway greenhouse effect. Mercury, in contrast, barely has an atmosphere at all. With just a wisp of exosphere made up of particles blown off by the solar wind, Mercury can't retain heat. That's why it has wild temperature swings from 430 to 800 during the day to 180 to 290 at night. But Venus never cools down. The atmosphere is so thick that heat has nowhere to go. The entire planet is essentially locked in a perpetual oven. Day or night, equator or pole, the temperature stays nearly constant across the entire surface. What's even stranger is how slowly Venus rotates. A single day on Venus, from one sunrise to the next, lasts 117 Earth days. And yet, the planet's temperature doesn't fluctuate much, because that ultra-dense atmosphere keeps everything wrapped in the same infernal warmth. The result is a hellish landscape, crushed by pressure, broiled by heat, and bathed in acid clouds. The Soviet Venera landers were the first to visit Venus's surface, and most didn't last long. Venera 13, the toughest of them, managed just 127 minutes before it succumbed to the brutal conditions, and despite all this, Venus was once considered Earth's twin. Similar size, similar gravity, and once, possibly, similar conditions. Some models suggest that Venus may have had oceans billions of years ago. But something changed. Volcanic activity, solar radiation, or other climate triggers may have led to the runaway greenhouse effect that transformed it into the inferno we see today. Which is why Venus isn't just fascinating, it's also a warning. It shows what happens when a planet's atmosphere traps too much heat, when the balance between incoming and outgoing energy tips too far. While Earth and Venus share many traits, their paths diverge dramatically. Studying Venus helps us understand the limits of climate stability, atmospheric chemistry, and planetary evolution. And it reminds us that proximity to the Sun doesn't always dictate temperature. It's the atmosphere, invisible from a distance, that tells the real story. Venus is farther from the Sun than Mercury, and yet it's the hottest world in the solar system, because sometimes what's on the outside matters less than what's trapped inside. You probably learned in school that Earth has just one moon. The moon, the big, bright, cratered rock that's been circling our planet for billions of years. And for most of history that was true. But it turns out Earth occasionally picks up a second moon, a smaller temporary visitor that gets caught in our gravity and sticks around for a while before drifting away. These are called temporally captured objects, or more affectionately, mini-moons. One of the most intriguing examples is an object called 2020 CD3. It was discovered in February 2020 by astronomers at the Catalina Sky Survey. At first, it looked like a tiny asteroid. Nothing unusual, but orbital calculations showed something weird. It wasn't just passing by Earth. It had been orbiting Earth for almost 3 years, completely unnoticed. That's right. Earth had a second moon, and we didn't even know about it. 2020 CD3 was small, roughly 1 to 3 meters across, about the size of a compact car. Far too dim to see with the naked eye. But it was real, and it had been looping around our planet since at least 2017, in a weird, corkscrew-shaped orbit influenced by both Earth and the Moon's gravity. By March 2020, it had escaped again, flung back into solar orbit by a gravitational nudge. But for a while, we had an extra moon, quietly circling Earth like a hitchhiker no one noticed. This wasn't the first time either. Back in 2006, astronomers spotted another object, 2006 RH120, which also spent several months orbiting Earth before departing. These mini-moons come and go, slipping in and out of orbit depending on the complex gravitational interactions between Earth, the Moon, and the Sun. They're usually tiny, too small to pose any danger and too unstable to stay for long. But their existence is a reminder that the Earth-Moon system is not as solitary as it seems. So how does this happen? Picture Earth cruising through the solar system with millions of small rocks, asteroids, debris, and space rubble zooming past. Occasionally, one of those rocks enters Earth's gravitational influence at just the right speed and angle. Instead of flying past, it gets temporarily captured. It starts orbiting Earth, held just barely by gravity, like a marble stuck in a bowl. But these orbits are usually chaotic and unstable. Solar tides, lunar gravity, and Earth's atmosphere, if the object dips too close, all conspire to pull the mini-moon away. Most only stay a few months or years before escaping. Still, scientists believe there are probably mini-moons orbiting Earth right now, too small or dim to be detected yet. New generations of wide-field sensitive telescopes, like the Vera C. Rubin Observatory, may help us spot more of these objects and track them better. And here's a fun twist. These captured objects could one day be perfect targets for exploration or resource mining. Because they're close, low mass, and often carbon-rich, mini-moons might offer easy access to raw materials. Think of them as cosmic stepping stones, little asteroids that swing in close enough for us to reach and study up close. They also raise deeper questions. What if one of these objects isn't natural? What if someday we discover that a mini-moon is actually a relic? An ancient probe, a piece of interstellar technology, or something we didn't expect? For now, though, they remain humble, tiny rocks, briefly bound to Earth, before drifting away again into the void. So, yes, Earth has a second moon. Occasionally, quietly, temporarily. And if you're lucky, you might be alive for the next one. This one sounds like pure sci-fi, the kind of thing you'd expect in a cartoon version of space. But it's absolutely real. There's a massive cloud drifting through the Milky Way that contains the chemical that gives rum its smell and raspberries their flavour. The cloud is called Sagittarius B2, and it sits near the centre of our galaxy, not far from the supermassive black hole known as Sagittarius A. It's a giant molecular cloud, over 150 light-years across, made up of gas, dust, and a cocktail of organic molecules. And among those molecules, something called ethyl formate. Ethyl formate is what gives raspberries their distinct fruity flavour, and rum its sweet, sharp aroma. And in 2009, a team of astronomers using the IRAM radio telescope in Spain detected this exact molecule, floating freely in deep space, over 25,000 light-years away. So yes, there's a giant gas cloud in the galaxy that contains the chemical flavour of fruit and alcohol. But let's be clear, you wouldn't want to breathe it in. Sagittarius B2 is also packed with formamide, methanol, hydrogen cyanide, and a long list of nasty chemicals you definitely don't want in your cocktail. This isn't a breathable or edible place. It's a frigid, radiation-bombarded cloud of raw chemistry. But the presence of complex organic molecules there is both fascinating and important. Because ethyl formate isn't simple, it's a relatively complex organic compound made of carbon, hydrogen and oxygen, and it suggests that prebiotic chemistry, the kind that leads to life, is not limited to Earth. In fact, these kinds of molecules seem to be forming all over the galaxy, even in cold, dark regions between stars. Astronomers have already found dozens of complex molecules in space, including amino acids, sugars and alcohols. Some of them are floating in comets, others are embedded in interstellar dust, and many, like ethyl formate, are drifting in clouds like Sagittarius B2, where stars are actively being born. That's the other twist here. Sagittarius B2 is a stellar nursery. Amid all those chemicals, new stars are forming, surrounded by disks of gas and dust, the same raw ingredients that once built Earth and the other planets, which means the seeds of life's chemistry are present before planets even form. It's not just cool, it's cosmic foreshadowing. Imagine this. A baby star lights up in the heart of Sagittarius B2, surrounded by gas laced with molecules that smell like rum and taste like fruit. Over millions of years, that star might gather a few planets. One of those planets might cool, and if conditions are right, those molecules might become something more, something like life. Now, No one's saying there's actual rum in space. Let's not push it. But the building blocks of organic chemistry are everywhere, and finding ethyl formate in deep space tells us that the universe is already doing the chemistry. Life doesn't start from zero. It starts with molecules that already know how to behave. And maybe the weirdest part of all, you have those molecules in you right now. Ethyl formate exists in tiny amounts in your own body. It's part of what gives certain foods their smell and taste. It connects raspberries, rum, and interstellar gas clouds in a single chemical through line. So next time you bite into a raspberry or sip something sweet, remember there's a cloud in the galaxy that tastes just like that, floating in the dark, waiting for the next star to be born. When we think of stars, we usually picture something like the sun, big, bright, blinding. But the sun, massive and essential as it is, isn't even close to being the biggest star out there. That title belongs to a class of stars called red supergiants, and the largest one we've found so far makes the sun look like a golf ball next to a beach ball. Meet UY Scuti, currently the best candidate for the title of largest known star by radius. UY Scuti is located about 9,500 light-years away in the constellation Scutum. It's a red supergiant with a radius estimated to be around 1,700 times that of the Sun. That number is almost meaningless until you put it in perspective, so let's do that. If you replaced our Sun with UY Scuti and placed it in the centre of our solar system, its surface would stretch well beyond the orbit of Jupiter, and possibly even close to Saturn. That means Mercury, vaporized, Venus, gone, Earth, obliterated, Mars, toast, Jupiter, deep inside the stellar atmosphere. We're talking about a star so massive in volume that it could contain more than 5 billion suns inside it, and yet it's not the most massive in weight. That's the weird part. UY Scuti is enormous in size, but it's surprisingly light for its size, weighing in at only 30 to 40 solar masses. It's kind of like a puffed up balloon, huge but not solid. Why? Because red supergiants are stars in their final phase. They've burned through most of their hydrogen, and now they're fusing heavier elements in a desperate attempt to stay alive. As they do, their outer layers expand dramatically and become unstable, resulting in their colossal size and low density. The outer atmosphere of UY Scuti is so thin and diffuse that if you were standing near the edge, ignoring the boiling plasma and fatal radiation, it might not even feel solid. It would be more like drifting through a fiery mist. Stars like this don't live long. In cosmic terms, UY Scuti is doomed. It's expected to eventually explode as a supernova, perhaps even a hypernova, an event that will outshine its galaxy for weeks and leave behind a neutron star or possibly a black hole. And here's the kicker. UY Scuti might not even be the largest star. It's just the largest we've measured accurately. Other candidates like Vivae Canis Majoris or Westerlund 126 may rival or even surpass it, but distance, dust and measurement uncertainty make these calculations tricky. As instruments improve, our rankings could change. Still, the existence of stars like UY Scuti stretches the limits of what we imagine a star to be. These aren't just glowing balls of gas. They're cosmic balloons that redefine scale. When you look at our Sun, it's hard to believe something 700 times larger could even stay intact, let alone shine. But UY Scuti proves it can. It reminds us that size in the universe is always relative. The Earth is big until you compare it to Jupiter. Jupiter is enormous until you look at the Sun, and the Sun is a heavyweight, until UY Scuti drifts into view like a red swollen giant silently pulsing at the edge of the galaxy. So next time you feel like you've seen the biggest thing ever, just remember, there's a single star out there that could swallow every planet we know and still have room for more. When a star explodes, that's usually the end of the story. A supernova is one of the most violent events in the universe, a dying star unleashing a burst of energy so intense it can outshine an entire galaxy for weeks. It's the dramatic finale of a star's life. Except, sometimes, it's not. Because in at least a few documented cases, stars have exploded and then kept on shining. These are the so-called zombie stars, celestial objects that, by all rights, should be dead. But somehow, they aren't. One of the most famous of these cosmic undead is IPTF 14HELs, discovered in 2014 by the Intermediate Palomar Transient Factory. At first, astronomers thought it was a typical Type II supernova. Big explosion, rapid fade. But this one didn't fade, not even close. It kept shining for over 600 days. That's 10 times longer than a normal supernova. And it wasn't just steady light. It fluctuated, brightening and dimming multiple times, almost like it was pulsing. That's not supposed to happen. A supernova is a one-time event. The energy runs out, the core collapses, that's the end. So how is this one still glowing? To make things even stranger, astronomers checked archival data and discovered that the same star had apparently exploded once before, back in 1954. Let that sink in. A star that exploded, survived, and exploded again. This behaviour defies our standard models of stellar death. One possible explanation involves something called a pulsational pair instability supernova, an extremely rare type of explosion that can occur in very massive stars, especially those 80 to 140 times the mass of the Sun. Here's the idea. In these stars, the core gets so hot that gamma rays, which normally help support the star against collapse, begin turning into pairs of electrons and positrons. This reduces internal pressure, causing the star to partially collapse. That collapse triggers a violent eruption, blasting off the outer layers, but not destroying the core. The result? The star explodes, but survives, at least temporarily. This can happen multiple times, with the star shedding layer after layer, until it finally reaches its limit and undergoes a full final supernova, or collapses directly into a black hole. It's a rare and bizarre process, but zombie stars like IPTF 14HELs seem to fit the pattern. Another possibility? Some theorists suggest these explosions might be powered by magnetars, ultra-dense neutron stars with magnetic fields trillions of times stronger than Earth's. If a magnetar forms in the heart of a supernova, it could act like an internal engine, injecting energy into the expanding material and keeping the explosion glowing far longer than usual. Whatever the case, these zombie stars shouldn't exist by conventional logic. They challenge what we thought we knew about how stars die, and they show that even in death the universe can get weird. They're also hard to spot. Most telescopes don't monitor supernovae for long periods. If you assume every explosion is a one-and-done event, you stop watching after a few weeks. But zombie stars need long-term observation, the kind we're only starting to prioritise now. Their discovery opens up new questions. How many stars die more than once? Could some supernovae we've written off be mid-transformation? Are we witnessing the birth of exotic remnants we've never seen before? In fiction, zombies come back to life and keep walking. In space they keep shining, long after their death sentence has been signed. And somewhere, right now, in a galaxy far away, another one may be glowing again. A light that should have gone out, flickering back to life. If you think Earth's weather is wild, with its hurricanes, hailstorms and heat waves, you haven't seen what the universe has to offer. Because about 63 light-years away, in the constellation Pegasus, there's a planet called HD 189733b. It's a gas giant, roughly the size of Jupiter, and it's become one of the most studied exoplanets in the galaxy. And the reason? It rains molten glass, sideways, at 5,000 miles per hour. Yes, seriously. HD 189733b is what astronomers call a hot Jupiter, a gas giant orbiting extremely close to its parent star. It's just 2.2 million miles from its sun compared to Earth's 93 million miles. That's so close, it completes an entire orbit in just 2.2 Earth days. As a result, the planet is tidally locked, meaning one side always faces the star, like how the moon always shows the same face to Earth. That sun-facing side gets scorched by constant radiation, while the dark side remains much cooler. This extreme temperature difference creates a nightmarish wind system. Hot gases rise on the day side and rush toward the cooler night side, creating super rotating winds that whip around the planet at over 5,400 miles per hour. That's 7 times the speed of sound. These are some of the fastest winds ever recorded on any known planet, and those winds carry something far more brutal than rainwater. The planet's blue colour, as seen by the Hubble Space Telescope, comes not from oceans or atmosphere like Earth, but from tiny silicate particles in the upper atmosphere. In the intense heat, those particles condense into molten glass, which then rains downward, only to be caught in the roaring horizontal winds and blasted sideways across the planet. Imagine standing in a storm where glass shards are flying horizontally faster than a fighter jet. Now imagine that you can't stand, because it's a gas giant with no surface, and the temperature is around 700 Celsius, 930 Kelvin. It's not just dangerous, it's completely inhospitable. But that's what makes it fascinating. HD 89733b was the first exoplanet where astronomers directly observed the colour of the atmosphere. It was also one of the first where we detected weather patterns on a world outside our solar system. Using spectroscopy, the analysis of light passing through the planet's atmosphere, scientists could identify the presence of silicates, methane, carbon monoxide, and other exotic compounds. This kind of research gives us a glimpse into just how diverse and strange alien worlds can be. While we often imagine Earth-like planets with oceans and skies, the universe offers no shortage of monsters like HD 89733b, where the laws of physics still apply, but the results feel ripped from science fiction. It also shows just how far we've come. Not long ago, exoplanets were purely theoretical. Now we're studying their weather, their chemistry, even the colours of their skies, and each new discovery expands the catalogue of possible worlds, not just those that could support life, but those that make our home world look shockingly gentle by comparison. HD 89733b is no place you'd want to visit, but it's a reminder that the universe isn't just strange, it's relentlessly creative, and sometimes it builds a planet where the skies scream, the rain cuts like blades, and the wind never stops. Most people think of a day as the time it takes a planet to spin once on its axis, and a year as the time it takes to orbit the Sun. For Earth, it's straightforward, 24 hours in a day, 365 days in a year. But Venus doesn't play by those rules. On Venus, a single day, one full rotation on its axis, lasts 243 Earth days. But its year, the time it takes to complete one orbit around the Sun, is only 225 Earth days. Let that sink in. A day on Venus is longer than its year. And it gets weirder. Venus rotates backwards, technically called retrograde rotation. While Earth and most other planets spin counterclockwise, as viewed from above the Sun's North Pole, Venus spins clockwise. So on Venus, the Sun would appear to rise in the west and set in the east, opposite of Earth. Combine the slow spin with the backwards rotation, and you get a truly alien experience. If you were somehow standing on Venus's surface, ignoring the crushing pressure, extreme heat, and sulfuric acid clouds, you would watch the Sun crawl across the sky in reverse, but so slowly you'd barely see it move for weeks. But why is Venus so strange? Astronomers think Venus didn't always rotate this way. It may have been hit by a massive object early in its formation, a planetary scale collision that slowed, tilted, and reversed its spin. Over time, the Sun's gravity exerted tidal forces on Venus's thick atmosphere, further slowing its rotation until it became the sluggish, backward-spinning world we see today. What's especially odd is that Venus's rotation is almost in perfect resonance with its orbit. A Venusian solar day, the time between two sunrises on the planet, is about 117 Earth days, which is almost exactly half of its 225 Earth day year. This creates a weird rhythm where the same side of Venus often faces Earth when they pass each other in orbit. It's a cosmic dance that's both elegant and bizarre. Now let's talk surface conditions, because this long day has brutal consequences. With the sun essentially hanging overhead for months at a time, the surface gets baked, reaching temperatures over 464 Celsius, 860 Celsius, hot enough to melt lead. Combine that with Venus's thick carbon dioxide atmosphere and runaway greenhouse effect, and you've got one of the most hostile environments in the solar system. Ironically, despite being called Earth's sister planet due to its similar size and mass, Venus is about as un-Earth-like as it gets. It spins slowly backward and blazes with unrelenting heat under a perpetual orange haze, and yet Venus fascinates scientists. Understanding why Venus spins the way it does, and how it developed such a radically different climate, helps us model the fates of other planets, including our own. Some researchers even think Venus might have been habitable billions of years ago, with oceans and mild temperatures, before tipping into the hellscape it is today. That raises a chilling thought. Maybe Earth and Venus weren't always opposites. Maybe they started from the same place, and Venus simply lost the climate lottery. So, to recap, one day on Venus, just 243 Earth days. 1 year on Venus, 225 Earth days. The sun rises in the west and sets in the east, and the planet itself might once have been almost like ours. But now it spins slowly through space, locked in its own strange rhythm, where time is stretched, motion is reversed, and days outlast years. Here on Earth, a year is 365 days long, a comfortable familiar loop around the sun. Even Mercury, the speedster of our solar system, takes 88 Earth days to complete a lap. But elsewhere in the galaxy, time moves a lot faster. Meet Ultracam J Carrion Kunto 9 plus U was 200b, an exoplanet so fast it orbits its star in just 18 Earth hours. That's not a typo. From sunrise to sunrise, if it even has sunrises, the entire year passes in less than a single day on Earth. 18 hours for an entire orbit. Every day is New Year's Eve. This planet belongs to a rare class known as ultra-short-period planets, or USPs, and they're exactly what they sound like. Worlds that whip around their stars on ridiculously short timescales. These planets are typically very close to their host stars, so close in fact that their orbits often lie just a few stellar diameters above the star's surface. Ultracam J Saturn 1+0200b, and others like it, orbits so tightly that it's subject to extreme tidal forces, relentless radiation, and temperatures that would vaporize rock. We're talking about 2000 degrees Celsius or 3600 degrees Celsius or more, hot enough to melt iron, shatter atmospheres, and potentially strip the surface down to its bare core. In fact, many of these fast-orbiting exoplanets may no longer be entire planets at all. Some scientists believe they're actually the leftover cores of gas giants, failed Jupiters that migrated inward toward their stars and had their outer layers blasted away by stellar radiation. What's left behind is a super-dense remnant, a rocky metallic world hugging its star with a death grip, orbiting at impossible speeds, glowing from the inside out. To complete an orbit in 18 hours, a planet must be moving at tens of kilometers per second, a pace that makes even Mercury look lazy. The gravitational dance is intense, and the proximity means the planet is likely tidally locked, with one side eternally facing its star and the other in permanent darkness. Imagine that for a moment. On one side you have a hemisphere of endless searing day, where the air, if there is any, is superheated plasma and the ground glows. On the other, a realm of freezing blackness, shielded from the star's fury, maybe cold enough for exotic ices to form from vaporized metal. We don't fully understand how planets like this survive. Some may not. They might spiral inward over time and be consumed by their stars, vaporizing in a final blaze. Others might stabilize in precarious balance, existing on a razor's edge of survival. But their discovery pushes our understanding of what a planet can be. For decades, astronomers assumed that close-in orbits like these were impossible. No planet could form there, or survive migration into that kind of heat, and yet we keep finding more. Ultra-short-period planets aren't just rare curiosities. They're telling us that planetary systems can be far more dynamic and violent than our own, and that maybe, just maybe, the rules we wrote for the solar system aren't the rules of the universe. So yes, there's a planet out there with a year that lasts just 18 hours. It circles its star in the time it takes us to binge-watch a show, cook dinner, and get through half a workday. And in that short span of time, it survives a cosmic gauntlet we can barely imagine. Every single day. Imagine holding a spoonful of material in your hand, just a teaspoon. Maybe it weighs a few grams, sugar, salt, water, whatever. Now imagine that same teaspoon weighs 1 billion tons. That's not science fiction. That's neutron star matter. The densest form of matter in the universe that still counts as a star, and not a black hole. Let's break it down. A neutron star is the collapsed core of a massive star, something at least 8 times the mass of our Sun, that has gone supernova. When such a star reaches the end of its life, it explodes in a cataclysmic blast that blows off its outer layers. What's left behind is the core, and under extreme gravity this remnant collapses so tightly that electrons and protons are forced to combine into neutrons. The result is an object made almost entirely of neutrons, compressed into an unimaginably small space. How small? A typical neutron star is only about 20 kilometers, 12 miles across. Roughly the size of a city, but it contains more mass than the entire Sun. That's like fitting all of Manhattan's skyscrapers into a single building, and then making it weigh as much as every structure on Earth combined. Times a few million. This crushing compression makes neutron stars absurdly dense. 1 cubic centimetre, about the size of a sugar cube, would weigh more than Mount Everest. And yes, a teaspoon of it would weigh around 1 billion tons. To put that in perspective, that's more than the entire mass of every car on Earth. More than 100 Mount Everests in your spoon. Enough mass to tear through the Earth's crust like a cannonball through tissue paper. If somehow it didn't annihilate everything on contact first. And here's the kicker. Neutron stars aren't even the final form of stellar collapse. If the core remnant is too massive, above about 2.1 solar masses, not even neutrons can hold back gravity. The whole thing collapses further into a black hole, so neutron stars are the last stop before the abyss, a balancing act between gravitational collapse and nuclear pressure. But they're not just heavy, they're fascinatingly weird. Because they're made of pure neutrons, they're governed by quantum mechanics, not just classical physics. Their surfaces are solid, maybe 1 meter thick, with crusts made of nuclear pasta, one of the strongest substances known in the universe. Underneath that crust is a superfluid neutron sea, spinning with near-frictionless precision. And spin they do. Some neutron stars, called pulsars, rotate hundreds of times per second, firing beams of radiation like cosmic lighthouses. These pulses are so regular they can be used as cosmic clocks, rivaling the precision of atomic timekeeping. Some of these pulsars are part of binary systems, locked in a death spiral with another star. They siphon material from their companion, grow heavier, spin faster, and sometimes explode again. Others collide with each other, creating gravitational waves and seeding the universe with gold, platinum, and other heavy elements, meaning your jewellery might literally come from the ashes of a neutron star collision. Neutron stars push physics to its edge. We don't fully understand what happens in their cores. Some models suggest the neutrons break down further, creating quark stars or strange matter, exotic states that we've never observed in a lab. So when we say, a teaspoon weighs 1 billion tons, we're not exaggerating. We're barely scratching the surface of how bizarre and extreme neutron stars really are. They are the densest stars in the universe, the stillborn hearts of supernovae. And a teaspoon of one is enough to humble a planet. Every night the moon appears quietly in the sky, serene, steady, always keeping the same face toward us. It's been that way for billions of years. It feels fixed, but it's not. In reality, the moon is drifting away from Earth. Slowly, steadily, relentlessly. And that tiny cosmic drift is changing time itself. Right now, the moon is moving away from Earth at a rate of about 3.8 centimetres, 1.5 inches per year. That might not sound like much, barely the width of your fingernail, but over millions of years it adds up. This isn't some random fluke, it's the result of a deep gravitational connection between Earth and the moon, a phenomenon called tidal locking and tidal friction. Here's how it works. The moon's gravity pulls on Earth's oceans, creating tides. As Earth spins, it drags those tidal bulges slightly ahead of the moon in orbit. That slight offset creates a gravitational torque that transfers rotational energy from Earth to the moon, slowing down Earth's spin and giving the moon a little boost, pushing it farther out. It's a cosmic trade-off. Earth spins more slowly. The moon moves farther away. And this exchange has been going on for billions of years. In fact, if you could go back in time, 1.4 billion years ago, a day on Earth lasted only 18 hours. When dinosaurs walked the Earth, a day was about 23 hours long, and in the far future, days will continue to get longer. Eventually, if nothing else intervenes, Earth's rotation will synchronize with the moon's orbit. That means one side of Earth will always face the moon, just like the moon already always shows the same face to Earth. At that point, Earth and moon will be tidally locked, permanently locked in a slow-motion gravitational embrace. But don't worry, that won't happen for billions of years. Meanwhile, scientists are tracking this lunar drift with incredible precision. Using retroreflectors placed on the moon by the Apollo astronauts, literal mirrors left behind on the surface, lasers are fired from Earth and bounce back, measuring the distance down to the millimetre. And what we're learning isn't just about the moon, it's about time. Because as the moon moves away and Earth's rotation slows, our days get longer. In the short term, that means we need leap seconds every few years to keep our atomic clocks aligned with the planet's rotation. In the long term, it means our concept of time, 24-hour days, 365-day years, is just a temporary balance. The moon is literally stretching our days. And it's not the only way it's shaped life on Earth. The moon's tidal influence helped regulate Earth's climate and stabilize its axial tilt, making seasons more predictable. Without the moon, Earth might wobble like a spinning top, with chaotic climate swings. In other words, we owe more to the moon than just poetry and moonlight. We owe it our stability, our timekeeping, and our very concept of a day. So next time you look up and see the moon hanging still in the sky, remember, it's not still at all. It's drifting away, slowly, steadily, reshaping the clock we live by. And in doing so, it's writing the future of time on Earth. Jupiter is a planet of extremes, the biggest, the most massive, the fastest spinning. But here's one of its most mind-blowing features. Its magnetic field is so powerful, it literally screams across space, and we can hear it. No, you won't hear it with your ears. There's no sound in space in the traditional sense. But Jupiter's magnetic field generates intense radio waves, bursts of electromagnetic energy so strong they can be picked up by antennas on Earth. And when those radio signals are converted into sound waves, they don't just make static. They howl, they whistle, they snap and crackle like thunder from another world. Let's rewind a bit. Jupiter's magnetic field, called a magnetosphere, is the largest structure in the solar system, stretching over 7 million kilometres toward the Sun and 600 million kilometres behind it, in a long tail that reaches past Saturn. That's bigger than the Sun itself. How is that possible? Because Jupiter is a spinning ball of metallic hydrogen. Hydrogen compressed under such extreme pressure that it behaves like an electrical conductor. As the planet spins, once every 10 hours, this metallic core generates a dynamo effect, creating a magnetic field 14 times stronger than Earth's. But it's not just the strength, it's the interaction. Jupiter's volcanic moon, Io, plays a huge role here. Io constantly spews out clouds of sulfur and plasma that get trapped in Jupiter's magnetic field. As these particles swirl through the magnetosphere, they generate intense radiation belts and trigger electromagnetic storms. The result is a kind of space weather system that sounds almost alive. NASA's Juno spacecraft, currently orbiting Jupiter, has captured these emissions using its WAVES instrument, which converts radio signals into audible sound. And the recordings are astonishing. Eerie whines, sharp crackles, and high-pitched tones that resemble the chirping of birds, distant lightning, or the sound effects from an alien movie. Some of these emissions are so strong, they were first detected by amateur radio astronomers decades ago, using ground-based antennas. In fact, under the right conditions, you can hear them with a homemade radio telescope in your own backyard. Jupiter's radio emissions fall into two main types: decametric, DAM radiation, typically influenced by Io's orbit, creating bursts that come and go in patterns; decymmetric, DIM radiation, more continuous, generated by electrons spiraling around Jupiter's magnetic field lines. These signals aren't just noise, they're data-rich, revealing how Jupiter's magnetosphere interacts with the solar wind, how its moons affect the system, and how radiation behaves in extreme environments. And they're not harmless. Jupiter's radiation belts are so intense that spacecraft like Galileo and Juno had to be carefully designed to survive them. Unprotected, the radiation would fry electronics in minutes. Even future human missions to Jupiter's moons, like Europa, will require serious shielding just to approach the planet. Jupiter isn't just a gas giant. It's a magnetic powerhouse, an electromagnetic monster roaring into the void. It creates a cosmic symphony, not of sound waves, but of radiation, plasma, and magnetism. A kind of space music that we can now translate and hear. And every time we do, it reminds us that the universe has a voice. It's not silent, it's singing. And sometimes, the loudest singer of all is Jupiter. Time feels like one of the few constants in life. Seconds tick by, hours pass, and we all seem to move forward through time at the same rate. But here's a fact that will twist your perception of reality. If you spend time on the top floor of a building, you age slightly faster than someone on the ground floor. That's not metaphor. That's Einstein's theory of general relativity at work, and it's been measured in real life. Let's unpack this strange truth. According to general relativity, gravity warps time. The stronger the gravitational pull you experience, the slower time passes for you, relative to someone in a weaker gravitational field. So the closer you are to a massive object like Earth, the more you're feeling gravity's pull and the more time is, ever so slightly, away being stretched for you. On the other hand, the farther away you are from the mass, like a few floors up in a high-rise, the less gravity you feel and the faster time ticks. This isn't just a theory, it's been proven experimentally. In 2010, scientists at the US National Institute of Standards and Technology, NIST, conducted a mind-bending experiment using two highly precise atomic clocks. They placed one clock just 33 centimeters, 13 inches, higher than the other, about the height difference between two shelves on a bookcase. The result? The higher clock ticked faster, only by about 90 billionths of a second per year, but still, it happened. And the only difference was the elevation. Gravity slightly weaker, time slightly faster. Now scale that up. If you live in a skyscraper or you work on the 30th floor of an office building, you are, very subtly, aging faster than someone in the lobby. Over a lifetime, the difference might only be a fraction of a second, but it's real. Astronauts on the International Space Station experience both effects. They're farther from Earth's gravity, which would make them age faster, but they're also moving incredibly fast. And special relativity says that motion slows time. So the two effects mostly cancel out. In fact, ISS astronauts age a bit slower overall compared to people on Earth, but the core idea remains. Time is not absolute. It bends, it stretches, it's elastic, depending on where you are and how fast you're moving. You and your friend might leave home at the same time, travel along different paths at different altitudes or speeds, and when you reunite, your clocks will disagree, just a little, and we've confirmed this over and over again. GPS satellites have to correct for this time distortion every second of every day. Because they orbit farther from Earth's gravity and move fast, both general and special relativity apply. Without constant correction, GPS would become useless within hours. So yes, when you take the elevator up, you're stepping into slightly faster time. You won't notice it, you won't feel it, but the laws of physics guarantee that it's happening. It's a quiet reminder that time, that thing we think is so fixed, so equal, so shared, is actually personal, unique, warped by gravity and motion. You're aging right now, but not at the same rate as the person above or below you. And if you want to squeeze just a little more time into your life, maybe ask for an office on the ground floor. It sounds like something ripped from a sci-fi movie or a billionaire's daydream. A planet made of diamonds, but it's real, and it exists about 40 light-years away in the constellation Cancer. Its name? 55 Cancri. This planet is one of the most bizarre and exotic objects ever discovered. A super-Earth, about twice the size of our planet and roughly 8 times more massive. But what really sets it apart isn't its size or orbit, it's what it might be made of. Let's start with the star. 55 Cancri E orbits a star called 55 Cancri A, and it does so incredibly close, just 2.4 million kilometers away. That's about 65 times closer than Mercury is to the Sun. It completes a full orbit in just 18 hours, meaning it has 2 sunrises a day. If it had a surface you could stand on. Because it's so close to its star, 55 Cancri E is blisteringly hot. Dayside temperatures are estimated to be around 2,400 Celsius, 4,300 gases, hot enough to vaporize rock. But it's not just the heat that makes it extraordinary, it's the chemistry. Spectral analysis of the star and modelling of the planet's interior suggest a carbon-rich composition, vastly different from Earth's silicon-oxygen-based makeup. Instead of iron cores and silicate mantles, this planet may have a carbon core surrounded by layers of graphite, and possibly a mantle of crystalline diamond. Yes, diamond. If the pressure and temperature conditions are right, and they seem to be, carbon deep within 55 Cancri could exist in solid crystalline form, forming vast deposits, or even a planet-scale structure of diamond. Now, to be clear, the entire planet isn't pure diamond, but calculations suggest that up to a third of its mass could be diamond. That's still a lot. More than Earth's entire biomass, oceans and atmosphere combined. In diamonds, it's a world of extremes, a surface of molten rock and blazing heat, a possible atmosphere of vaporized minerals constantly being blown off into space, and deep inside, a heart of sparkling carbon crystal, locked beneath a surface so hot it glows. And here's a twist. 55 Cancri might be tidally locked, with one side always facing its star. That would mean a permanent day side, blazing with infernal temperatures, a night side, possibly cool enough for exotic elements to condense or settle, or not depending on atmospheric circulation. But what truly makes this planet a showstopper isn't what it offers to mining billionaires, it's what it says about the diversity of the universe. Our solar system is built from oxygen, silicon, iron, water, but in other places, where stars and planets form from carbon-rich gas clouds, entirely different chemistries emerge. carbon dominates, and carbon, under pressure, becomes diamond. So it turns out planets don't just come in rocky, gaseous or icy varieties, they can be gemstones, forged in gravity, wrapped in fire, gleaming in the darkness. We'll probably never walk on 55 Cancri. Its heat would kill, its radiation would fry, its gravity would crush. But it sparkles in our imaginations, proof that the universe doesn't care about our rules. It creates worlds we can't yet visit but can marvel at from afar. And yes, there really is a planet out there made of diamonds. When you think of lakes and rivers in the solar system, Earth is probably the only world that comes to mind. Oceans, rainfall, shorelines, these are distinctly earthly things. But that's where Titan, Saturn's largest moon, changes everything. Because Titan has lakes, rivers, rain, and even seas. Only they're not filled with water. They're filled with liquid methane and ethane, hydrocarbons that are gases on Earth, but on Titan, they act like water does here. Let's zoom in. Titan is the second largest moon in the solar system, bigger than Mercury, nearly the size of Mars. It has a thick atmosphere composed mostly of nitrogen, with traces of methane. In fact, it's the only moon with a dense atmosphere, thick enough to hide the surface completely from view in visible light. For decades, Titan was a mystery. Then, in 2004, NASA's Cassini spacecraft arrived at Saturn and sent a probe, Huygens, plunging through Titan's orange clouds. What it found was astonishing. The surface of Titan showed drainage channels, riverbeds, shorelines, and pebbles rounded by liquid erosion. Using radar mapping, Cassini later confirmed the presence of massive lakes and seas, mostly clustered around the moon's poles. Some of them are hundreds of kilometers wide, larger than Lake Superior. The liquid filling these lakes is not water. Titan is far too cold for that. Surface temperatures hover around 179 to 290 degrees. Water here is rock-hard ice. Instead, the lakes are composed of liquid methane and ethane, gases that condense into liquids at Titan's frigid temperatures. It's a fully functioning hydrological cycle, just like Earth's, but using entirely different chemistry. Methane evaporates from the lakes. It forms clouds in Titan's atmosphere. Those clouds rain methane back down onto the surface, filling rivers, carving canyons, and feeding the lakes again. It even has seasons. As Titan orbits the Sun with Saturn, sunlight shifts across its poles, triggering storms, monsoons, and lake-level changes. There's even evidence of waves lapping at the shores, suggesting some of Titan's lakes aren't just puddles, but dynamic, moving bodies of liquid. And perhaps the most haunting thing, if you stood on the edge of one of Titan's seas, say Kraken Mare, you'd see a dark, glassy surface stretching into the mist. It wouldn't look like water. There'd be no blue reflection. But it would move, and possibly even smell faintly of gasoline. Despite its alien chemistry, Titan is one of the most Earth-like worlds we've ever found, in shape, structure, and climate systems, which is why it's a key target for future exploration. In fact, NASA is planning to launch a mission called Dragonfly in 2028, a nuclear-powered rotorcraft that will fly through Titan's skies, hopping from location to location, studying its chemistry and potential for life. Because here's the big question: could life exist in those methane lakes? It wouldn't be life as we know it. But some scientists believe methane-based biochemistry is theoretically possible. Life that doesn't use water but liquid hydrocarbons. Life that breathes hydrogen or metabolizes ethane. If Titan harbours life, even microscopic, alien life, it would prove that biology can arise under entirely different conditions, that life is not a fluke of Earth, but a common consequence of chemistry in the universe. So yes, Titan has lakes, rivers, rain, clouds, seas, but it doesn't need water to do it. It writes its own script. It's a frozen orange world where methane flows like water and the rules of Earth get rewritten. When we think about our solar system, we tend to picture a balanced community of planets, from Mercury all the way to Neptune, each with its own moons, rings and unique quirks. Maybe we give a little extra weight, pun intended, to gas giants like Jupiter and Saturn because they're huge compared to Earth. But here's the reality. The Sun absolutely dominates everything. In fact, the Sun contains 99% of all the mass in the solar system. That's not an exaggeration. It's an almost unfathomable truth. All the planets, moons, asteroids, comets, dust, and even that gas giant Jupiter, they collectively make up only 0.2% of the total mass. Let's put some numbers behind it. The mass of the Sun is about 1.989 x 1030 kilograms. Jupiter, the biggest planet by far, weighs in at 1.898, 10 to the 27 kilograms. That's roughly 0.1% of the Sun's mass. Earth, just 0.013%. We're rounding errors in a system that's overwhelmingly solar, and the gravitational consequence of that dominance is huge. The Sun's sheer mass is what allows it to hold the entire solar system together. It's why planets orbit in predictable ellipses. Comets return after centuries-long journeys. The asteroid belt exists. Even distant objects in the Oort cloud, possibly a light year away, still feel the Sun's gravitational influence. In essence, the solar system isn't a system of planets around a star. It's a star with a few planetary sidekicks. And yet, despite being so massive, the Sun is not even particularly large on a galactic scale. It's classified as a G-type main sequence star, a fairly ordinary middle-aged star. There are many bigger stars, more massive stars, hotter stars. But in our little corner of the galaxy, the Sun is everything. Its mass drives its energy, and that energy is immense. Inside the Sun's core, hydrogen atoms are being fused into helium at a rate of 600 million tons per second, converting about 4 million tons of that mass into pure energy every second. That's what fuels sunlight, solar wind, and the light that takes just over 8 minutes to reach Earth. And without that mass, there's no fusion, no light, no heat, no life. Interestingly, the fact that planets formed at all is due to leftover material. After the Sun formed from a collapsing cloud of gas and dust, it gobbled up most of the mass. What didn't get pulled in flattened into a protoplanetary disk, which eventually coalesced into planets, moons and asteroids. So the solar system is really just Sun leftovers. The massive centre remains, a fiery engine that dwarfs everything else, shaping the orbits, climates and fates of every object in its grip. Even Jupiter, enormous, gravitationally dominant with dozens of moons, is just a rounding error in comparison. Next time you look up at the sky, remember, everything we know, everything we are, every story we've ever told, is happening in a system where one object owns 99% of everything. The Sun isn't just the centre of our solar system, it is the solar system. When you look up at the night sky and see the Milky Way stretched like a ribbon of light, it's hard not to be overwhelmed by the sheer number of stars. Billions of them, maybe hundreds of billions. So here's a fact that sounds completely backwards, but is totally real. There are more trees on Earth than stars in the Milky Way. A 2015 study published in Nature estimated the number of trees on Earth at around 304 trillion. That's trillion with a T. Not billion, trillion. That means on average there are about 420 trees per person on the planet. Now compare that to our home galaxy. Astronomers estimate that the Milky Way contains somewhere between 100 billion and 400 billion stars. That's a mind-bending number, but it's still less than a trillion. So even if we take the high end and say the Milky Way has 400 billion stars, Earth still has 7 to 8 times as many trees. Let that sink in. This blue and green rock floating through space, this little corner of the universe, holds more individual trees than there are stars lighting up the spiral arms of an entire galaxy. It flips your expectations, doesn't it? Because when we think of the cosmos, we assume scale automatically favours the stars. The galaxy is so much larger, so much more ancient, so much more vast. But trees? Trees are everywhere, from boreal forests in Russia and Canada to rainforests in the Amazon and Congo, from mountain pines to desert acacias to the palm trees lining city streets. Trees fill the continents, cling to slopes, crowd river valleys. They aren't just scenery, they're a global phenomenon. Now, let's be clear, this doesn't mean trees are more important than stars. It's not a contest of cosmic value. But it does remind us that sheer numbers don't always scale the way we expect. Stars feel infinite. Trees seem finite. But here on Earth, they thrive in trillions. And the story behind that number is just as fascinating. For decades, estimates of the number of trees on Earth were far too low, often in the tens of billions. But researchers from Yale University combined satellite data, forest inventories, and ground-level observations across 400,000 sample plots worldwide to build the most accurate model ever. The result, over 3 trillion trees, with the largest concentrations in tropical and boreal forests. But here's the twist. We're losing them. That same study estimated that humans cut down around 15 billion trees per year, and while about 5 billion new trees are planted or naturally regenerated each year, the net loss is still around 10 billion trees annually. That means we've lost nearly half the trees that once existed on Earth. So yes, we have more trees than stars in our galaxy, but that balance is changing, and it's a powerful reminder that while the universe creates in cosmic quantities, we are stewards of one small part of it. We can't reach the stars yet, but we walk among the trees, and every one of them, every trunk, every leaf, is part of a number so big it outshines even the Milky Way. When you think of the coldest place in the universe, you probably imagine some distant, empty corner of deep space, billions of light years away, untouched by stars or heat or even time. And that wouldn't be a bad guess. But it wouldn't be the right one, because the coldest known place in the universe is here, on Earth, in a lab. Let's rewind. Space is cold, very cold. In the vast empty regions between galaxies, where there's no starlight, no radiation, and almost no particles, the temperature hovers around 2.7 Kelvin. That's 270,45 or 454.8 you wonder. Just a hair above absolute zero, the point at which all molecular motion stops. But here's the thing, we've actually beaten that. In laboratories around the world, especially in places like MIT and Germany's Max Planck Institute, physicists have used advanced techniques to cool atoms to temperatures below a billionth of a degree above absolute zero. That's 0.001 K, colder than anything naturally occurring in the entire universe. How? It all comes down to laser cooling and magnetic traps. Atoms, by definition, move. That movement is what we perceive as heat. To cool them, scientists shine precisely tuned lasers at the atoms. These lasers slow the atoms down by applying opposing forces, draining their kinetic energy. Then, magnetic fields are used to trap the atoms in place, preventing them from moving at all. The result is a special state of matter called a Bose-Einstein condensate, a cloud of atoms so cold they begin to act as one unified quantum entity. Instead of behaving like individual particles, they merge into a kind of superatom, with bizarre quantum properties that are still being studied today. These ultra-cold environments are used for cutting-edge research, like simulating black holes and early universe conditions, studying quantum entanglement and wave functions, creating incredibly precise atomic clocks and sensors. In 2018, NASA even launched the Cold Atom Lab aboard the International Space Station, the first facility to create Bose-Einstein condensates in microgravity. Without gravity pulling on the atoms, scientists can keep them stable for longer, allowing even colder, purer states to be reached. But let's pause for a second. We, fragile human beings, have reached temperatures lower than the natural floor of the cosmos. That's like digging a hole deeper than the bottom of the ocean, and doing it with beams of light and magnetic fields. And why does that matter? Because cold is a gateway to the quantum world. At ultra-low temperatures, classical physics gives way to quantum behaviour. Atoms become waves, probabilities become reality, time and position blur. In other words, to understand the most fundamental truths of the universe, we first have to freeze it. So while the universe can bake planets, forge stars and light up galaxies, it's here on Earth, in tiny vacuum chambers surrounded by coils and lasers, that the coldest extremes are found. We didn't just go colder than space, we went colder than nature itself. Black holes are the monsters of the universe. They devour stars, warp time, and trap light itself. But one of the weirdest things a black hole can do to you, turn you into spaghetti. And yes, the actual term for this, used in physics journals and astrophysics textbooks, is spaghettification. Let's break it down. Imagine you're falling into a black hole. You're drifting feet first, peacefully at first. But as you get closer, you begin to feel stretched. That's because of tidal forces, the difference in gravity between one part of your body and another. On Earth, we experience this when the moon pulls more on the oceans facing it than on the far side, creating tides. But with a black hole, it's a whole different level. Let's say your feet are just a few kilometers closer to the black hole than your head. That slight difference in distance causes the gravitational pull on your feet to be significantly stronger than the pull on your head. So your body starts to stretch vertically. At the same time, the black hole's gravity is compressing you inward from the sides, horizontally. The result is a surreal process where you're stretched into a long, thin strand while being squeezed from every direction. Scientists call this effect spaghettification because, well, that's exactly what you become. A cosmic noodle. If the black hole is small, the spaghettification happens well outside the event horizon, the boundary beyond which not even light can escape. You'd be torn apart before you ever crossed it. But if it's a supermassive black hole, like the one at the centre of our galaxy, the tidal forces near the event horizon are weaker, at least initially. In theory, you could cross the horizon without noticing, and only experience the noodle treatment as you drift closer to the centre. It sounds like sci-fi. It sounds ridiculous. But it's real physics, backed by Einstein's theory of general relativity and confirmed by the equations governing gravitational gradients. The story doesn't end with the stretch either. Once you pass the event horizon, you're in a region where space and time switch roles. Going forward in time now means moving deeper into the black hole. No matter what you do, you're pulled inward, not because you're being sucked, but because your future lies at the singularity, and you can't avoid your future. Eventually, the spaghettified version of you reaches the singularity, the infinitely dense point at the black hole centre where space-time itself breaks down. Physics, as we know it, ceases to function. So, is there any way to survive spaghettification? Short answer, no. Long answer, still no, unless we discover some new laws of physics or exploit hypothetical phenomena like wormholes or exotic matter. As of now, once you cross that line, your fate is sealed, and your shape, well, stretched. But while it's terrifying, it's also awe-inspiring, because spaghettification is a perfect example of how extreme the universe can get. It's not fantasy or horror fiction, it's just gravity, doing its job at scales and intensities we can barely imagine. And the fact that physicists had to invent a word that sounds like something from an Italian cookbook, that just adds a sprinkle of cosmic humility. So yes, a black hole can and will turn you into spaghetti. It's weird, it's real, and it's science. Mercury, the innermost planet of our solar system, is already a strange little world. It's airless, scorched by the sun, riddled with craters, and swings around its orbit like it's late to everything. But here's a fact that bends brains. A day on Mercury is longer than a year. Yes, really. Mercury takes about 88 Earth days to complete a full orbit around the Sun. That's one Mercurian year. But a single day on Mercury, meaning the time it takes for the Sun to return to the same spot in the sky, called a solar day, lasts about 176 Earth days. In other words, the Sun rises on Mercury only twice per year. So, if you were standing on the surface of Mercury, preferably in a very good heat suit, you'd see the Sun rise. And then watch it slowly crawl across the sky over the course of nearly 6 Earth months, before it finally sets. Even stranger, Mercury is not tidally locked. That's the phenomenon where one side of a celestial body always faces another, like how the Moon always shows Earth the same face. Instead, Mercury is in a bizarre state called a 3-2 spin-orbit resonance. Here's what that means. Mercury rotates 3 times on its axis for every 2 orbits around the Sun. That's why its rotation period, the time it takes to spin once, is 58.6 Earth days, while its orbital period is 88 days. That ratio causes the Sun to do something wild in Mercury's sky. Because of Mercury's highly elliptical orbit, its speed around the Sun changes dramatically. Near perihelion, closest to the Sun, it speeds up. Near aphelion, farthest from the Sun, it slows down. And combined with its rotation, that means that for some regions on Mercury the Sun appears to rise, stop, reverse course for a while, and then resume its path across the sky. Imagine that. The Sun rises slowly, then it stops, then it backs up, then it goes forward again. All because Mercury's rotation and orbit are locked in a cosmic rhythm that warps time, light and motion into something deeply weird. And the consequences don't stop at the visuals. This 3-2 resonance also influences Mercury's extreme temperature swings. The planet has no real atmosphere to trap heat, so the side facing the Sun bakes at over 430 degrees, 800 degrees, while the night side plummets to 187, 290 degrees. The long days and nights stretch these extremes over months at a time. You'd be forgiven for thinking Mercury is boring. It's small, grey, no moons, no rings, but its internal dynamics, completely unique. No other planet in the solar system has this kind of orbital dance, a blend of rotational quirks, gravitational influence from the Sun, and timing so precise it took spacecraft like Messenger to fully decode. So to recap, Mercury's year, they last 88 Earth days. Its day, sunrise to sunrise, there are 176 Earth days. It rotates 3 times for every 2 orbits. It's not tidally locked, but it behaves like it is, at first glance, and in this quiet, cratered world the Sun itself seems to hesitate. Rise, reverse, resume, all while Mercury dances to a beat entirely its own. The Moon seems close. You look up and there it is. Bright, familiar, almost touchable. But here's a jaw-dropping fact. You could fit every planet in the solar system, from Mercury to Neptune, side by side between Earth and the Moon, and still have room left over. Seriously, let's do the math. The average distance from Earth to the Moon is about 384,400 kilometres, roughly 238,955 miles. This is called the lunar distance, and it's our constant companion in spaceflight astronomy and sci-fi storytelling. Now let's line up the diameters of each planet. Mercury, 4,179 km Venus, 12,104 km Mars, 6,779 km Jupiter, 113,20 Saturn, 116,460 km Uranus, 50,724 km Neptune, 14,254 km. Add those up and you get 380,010 kilometers. That's about 4,400 kilometers less than the Earth-Moon distance. So yes, line them up like marbles. From tiniest Mercury to massive Jupiter, and you could slide all 8 planets neatly between Earth and the Moon, and still have a few thousand kilometers to spare. Enough space for Pluto, some moons, and a healthy buffer zone. Let's be clear, this isn't saying you could actually do it. Gravitational forces, orbital mechanics, and celestial collision warnings aside, It's not physically possible to pile the planets together like that, but it's a stunning way to reframe space, because the Earth-Moon distance feels short. We've sent astronauts there. It takes light just over a second to make the trip, but in that single stretch of cosmic real estate, you could fit the entire planetary family. The solar system suddenly feels a lot more compact, and a lot more immense, all at once. This fact also highlights just how small the planets really are compared to the distances between things in space. Even giant Jupiter, the largest planet by far, is only about a third of the total width between Earth and Moon. In space, size is relative, and space is really good at making everything feel small. It also puts our Moon into perspective. The Moon is 384,400 kilometers away, but it's only 3,174 kilometers in diameter, less than the width of Australia. Yet it's the fifth largest moon in the solar system and one of the brightest objects in our night sky. In a way, this fact captures the essence of astronomy. What feels distant may not be as far as we think. What feels massive may be dwarfed by the space around it. And what seems simple, like the gap between Earth and the Moon, turns out to be surprisingly roomy. So next time someone tells you the Moon is just up there, you can smile and say, sure, just far enough to fit every planet in the solar system between us, and still leave room for dessert. One of the first questions kids, and adults, ask about the universe is deceptively simple. Where is the edge? Or, where did it all begin? Followed inevitably by, what's it expanding into? And the answer is stranger than you expect. The universe has no edge, and it has no centre either. Let's unpack that. When we say the universe is expanding, we don't mean it's growing outward into some empty void like a balloon inflating inside a room. There's no outside of the universe. The expansion isn't happening into anything. It's space itself that's expanding, stretching, everywhere, all at once. Think of it like this. Imagine the surface of a balloon. Now put dots on the balloon. Those dots are galaxies. As you blow up the balloon, the surface stretches. The dots move away from each other. But here's the key. There's no centre on the surface of the balloon. There's no edge either. You can walk in any direction forever and never fall off. The universe is like that, except in 3 dimensions. Well, more than that if we're being fancy with math. The Big Bang didn't happen at a point in space. It happened everywhere in space. It was a moment, not a location. Every region of the universe we observe, near, far, and unimaginably distant, originated in the same event. So when we say the universe is expanding, what we mean is every region of space is growing, every galaxy on large enough scales is moving away from every other, and there is no privileged spot, no cosmic centre. You're not at the centre, neither is Earth, neither is any other galaxy. From any galaxy's point of view, it looks like everything else is receding. That's how space works when it stretches uniformly. Here's the mind bender. Even though galaxies are moving apart, they're not moving through space. The space between them is what's growing. And if that doesn't scramble your brain, consider this. You can't travel to the edge of the universe because there is no edge. It's not like a sphere you can stand on the outside of. The universe may be finite or infinite. We're still not totally sure. But either way, it has no boundary in the way we understand it. What about shape? Some models suggest the universe is flat, like an infinite sheet. Others suggest it's closed, like a 4-dimensional sphere. You could travel in one direction forever and end up back where you started. And some models allow for a hyperbolic or saddle-shaped universe. But in all those models, there's still no edge, no wall, no sign that says, you are now leaving the universe, and the centre. If you're imagining a big bang like a firework exploding outward from a central point, that's the wrong image. The Big Bang was the expansion of space itself, not an explosion in space. So there was no centre then, and there's no centre now. This is what makes cosmology so humbling, and so thrilling. The universe doesn't behave like anything we evolved to understand. We live in a world of edges, boundaries, and reference points. But space and time don't play by those rules. So when you look up at the night sky and wonder where it all began or where it all ends, remember there's no edge to fall off, no center to point at, just an expanding, boundless cosmos that somehow includes you, right now, asking the question. Our galaxy, the Milky Way, isn't sitting still in space. It's flying at incredible speed. Right now, this very second, you, your chair, your city, this planet, are all hurtling through the universe at over 600 kilometers per second. That's 1.3 million miles per hour, toward a mysterious location in the sky. This motion isn't random. It's not from the Milky Way spinning. We're being pulled by something we call the Great Attractor. And here's the weird part. We don't really know what it is. Let's rewind. Astronomers have known for decades that galaxies aren't just moving because of cosmic expansion. On top of that expansion, they have peculiar velocities, additional motions caused by local gravitational influences. When scientists mapped these motions across the sky, they noticed a strange anomaly. A whole swath of galaxies, including our own, are moving toward the same region of space, a dense patch of the sky in the direction of the Centaurus and Hydra constellations. This movement is not explained by the expansion of the universe. It's gravitational. Something is there. Something huge. They called it the Great Attractor, not because it's flashy or dramatic, but because its gravitational pull is so powerful that it's drawing in entire galaxy clusters, including the Milky Way, the Andromeda Galaxy, the entire Laniakea supercluster, which spans 500 million light-years. That's right. Our whole galactic neighbourhood is being dragged across the universe like a leaf caught in a current. But here's where it gets maddening. We can't see it clearly, because the Great Attractor lies in the zone of avoidance, the part of the sky blocked by the dense stars and dust of our own Milky Way's plane. It's like trying to stare into a spotlight through a fog machine. We know something massive is there, but we don't know what it looks like. What we do know is this. The gravitational pull in that region suggests a mass tens of thousands of times larger than the Milky Way. Some of it may be part of a gigantic galaxy cluster called the Norma Cluster, and even that may be just a small piece of an even bigger puzzle. Later research discovered that the Great Attractor is just one part of a larger flow, toward a structure called the Shapley supercluster, possibly the most massive cluster of galaxies in our observable universe. So picture this. Earth orbits the Sun. The Sun orbits the Milky Way. The Milky Way drifts through a local group of galaxies. That group is sliding toward the Great Attractor, and the Great Attractor might itself be falling into the gravity well of the Shapley supercluster. It's motion on top of motion, on top of more motion, all playing out across hundreds of millions of light years. And the cause of that motion, still mostly invisible. Dark matter probably plays a big role. So does the web-like structure of the universe itself. Filaments of galaxies and clusters woven together by unseen gravity. But the full nature of the Great Attractor remains one of the most intriguing cosmic mysteries. We know it's real. We know we're headed straight for it. But we still don't know exactly what it is. So the next time you look up at the stars and feel like you're not moving, remember, you're not just spinning on a planet orbiting a star. You're part of a galaxy that's racing toward an invisible titan in space. One we can't yet see, one we don't fully understand, and it's pulling us in. Venus is often called Earth's sister planet. It's roughly the same size, similar in mass, and it's our closest planetary neighbour. But that's pretty much where the similarities end. Because Venus isn't just hostile, with scorching heat, crushing pressure, and sulfuric acid clouds. It also has one of the weirdest rotations in the entire solar system. Here's the fact. Venus spins backwards. and its day is longer than its year. Let's break that down. Venus rotates retrograde, meaning it spins in the opposite direction of most other planets. If you could hover above the solar system, you'd see Earth spinning counterclockwise, like most planets, but Venus spinning clockwise. So if you were standing on Venus and somehow didn't instantly die, the sun would appear to rise in the west and set in the east, the reverse of what we see on Earth. Now let's talk about that day. One full rotation of Venus, one sidereal day, takes about 243 Earth days. That's the time it takes Venus to turn once on its axis. But Venus orbits the Sun, one Venusian year, in about 225 Earth days. So yes, a single day on Venus is longer than its year, even weirder, due to the way its slow rotation and orbital motion interact. A solar day on Venus, the time from one sunrise to the next, is about 117 Earth days. So in Venus time, the planet orbits the Sun faster than it spins. The Sun rises in the west, crawls across the sky for months and sets in the east, and all of that happens in an atmosphere so thick it rotates 60 times faster than the surface, creating permanent global hurricane conditions. So, what happened? Why does Venus spin this way? No one knows for sure, but scientists have some ideas. A massive collision early in Venus's formation might have flipped its rotation. Or tidal interactions between Venus and the Sun could have gradually slowed and reversed its spin over time. Another theory: it never spun much in the first place, and the slow retrograde motion is the result of complex atmospheric and gravitational effects. What we do know is that Venus's rotation is extremely slow and unusual, and its surface conditions are the most hellish of any planet. We once thought Venus might be lush, maybe a jungle world. That idea was popular in the early 20th century before we had real data. Then we sent probes, and what we found was a runaway greenhouse effect with temperatures around 465 Baden, 860, hot enough to melt lead, surface pressure 92 times greater than Earth's, like being a kilometre underwater, clouds made of sulfuric acid, and wind speeds in the upper atmosphere that move faster than the planet itself spins. So let's recap. Venus spins backward. One rotation takes 243 Earth days. One orbit takes 225 Earth days. A solar day, sunrise to sunrise, is 117 Earth days. And the Sun rises in the west, not the east. It's the slowest spinner in the solar system, and one of the strangest. Venus may be our sister in size, but in almost every other way it's the upside-down version of Earth. Space feels distant, mysterious, unreachable. We think of rockets, space stations, launch pads, countdowns. Like space is a destination that only the boldest can reach after years of planning. But here's the wild truth. Space isn't that far away. If you could drive straight up, no traffic, no atmosphere, no engineering limits, you could get to space in about an hour. Seriously, let's define what we mean by space. The internationally accepted boundary of space is known as the Kármán line, located at an altitude of 100 kilometers, 62 miles, above sea level. That's the point where Earth's atmosphere becomes so thin that conventional aircraft can no longer generate lift, where space technically begins. So if you hopped into a car and drove vertically at a steady 100 km/h, about 60 mph highway speed, you'd cross into space in 1 hour. That's less than most morning commutes. It's shorter than an average movie. You could be in space before your coffee gets cold, in theory. Now, of course, we can't actually drive straight up. Gravity doesn't work that way. Cars don't fly. And even if they could, they're not equipped to handle the vacuum, radiation, or extreme temperatures of space. But that doesn't change the fact that space is astonishingly close, a thin veil above our heads. To put this into even more perspective, the stratosphere begins at about 10 to 15 kilometers. Commercial airplanes fly around 9 to 12 kilometers up. Mount Everest tops out at just under 9 kilometers. The edge of space is only 10 times higher than a jumbo jet's cruising altitude. In the grand scale of Earth, or the solar system, or the universe, 100 kilometers is a rounding error. It's nothing. If Earth were shrunk to the size of a standard globe, space would be about the thickness of the varnish on the surface. But crossing that boundary changes everything. The moment you pass the Kármán line, you're in microgravity. The sky turns black. You're above 99.9% of Earth's atmosphere, and you're officially an astronaut. This is why suborbital flights, like those from Blue Origin's New Shepard or Virgin Galactic's Spaceship Two, can launch passengers to space without going into full orbit. They just go up and down like a ballistic arc. And it only takes a few minutes to cross that invisible line. Space tourism is built on this very principle, that space is nearby, but escaping Earth's gravity well and staying in orbit is the real challenge. That's why the International Space Station, which orbits at around 400 kilometers, requires speeds of 28,000 km/h, 17,500 to stay up there. That's why full orbital rockets are massive, complex machines, and why going to the Moon, or Mars, is an entirely different beast. But still, getting to the edge of space, that's not science fiction anymore. That's within the reach of your morning commute, distance-wise anyway. So next time you look up, remember, you're not stuck on Earth. You're living right next door to space. And if you had the right vehicle, you could be there by lunch. You've heard of black holes, you've heard of white dwarfs, but neutron stars, those might just be the most extreme objects in the universe that don't collapse into nothingness. And here's one of the most mind-melting facts about them. A single teaspoon of neutron star material would weigh about 1 billion tons. Let's unpack that, and try not to flatten ourselves under the weight of it. What is a neutron star? A neutron star is the ultra-dense core left behind after a massive star explodes in a supernova. When that star runs out of fuel, its outer layers blow away in a violent detonation, but its core collapses in on itself. If it's not quite massive enough to become a black hole, gravity stops it just shy of that, and squeezes it into a neutron star. This thing is only about 20 kilometers wide, roughly the size of a city, but with a mass greater than the Sun. Imagine the Sun. Now cram it into Manhattan. That's a neutron star. So, why is it so heavy? Because the matter inside a neutron star is unlike anything else. In the collapse, electrons and protons are forced together, merging into neutrons. The result is an object made almost entirely of neutron-rich material, matter so densely packed that the atoms themselves don't survive. There's no space between particles. It's a quantum stew of subatomic leftovers. The density of a neutron star is about 4s1017 km/m3. That's equivalent to the entire human population compressed into the volume of a sugar cube. Which brings us back to the spoon. Take just 1 cubic centimetre, about a teaspoon, of neutron star matter and bring it to Earth. Hypothetically, since it would instantly crush, explode and destroy everything in sight. That spoonful would weigh about 1 billion tons, more than the mass of every building on Earth combined. And it gets crazier, the gravity of a neutron star. Because of all that mass packed into such a small volume, the surface gravity of a neutron star is over 100 billion times stronger than Earth's. If you stood on one, again don't, you'd be crushed into a layer of atoms thinner than a credit card in a fraction of a second. Even light is bent dramatically by a neutron star's gravity. You can see the far side of a neutron star curved around to face you, thanks to this extreme warping of space-time. And let's not forget about magnetars, a special kind of neutron star with magnetic fields trillions of times stronger than Earth's. They can distort atoms, strip spacecraft electronics from thousands of kilometers away, and occasionally blast gamma-ray flares so intense they've affected Earth's atmosphere from across the galaxy. Why does this matter? Because neutron stars are laboratories of the most extreme physics imaginable. They let us study matter at densities we can't recreate on Earth. The behaviour of quantum particles under crushing pressure. gravitational waves from collisions between neutron stars, as first detected in 2017, and maybe even the mysterious substance called quark gluon plasma. If you go deep enough inside, they are cosmic fossils, ancient remnants of massive stars floating across the galaxy like spinning tombstones. And they're beautiful too. Some neutron stars spin hundreds of times per second, emitting radio waves like a lighthouse beam. We call these pulsars. The first ones ever discovered were so regular, scientists thought they might be signals from aliens. Turns out they were just dead stars with incredible rhythm. So yes, a teaspoon of neutron star would crush a skyscraper flat. It would weigh 1 billion tons, and it would remind us that the universe is capable of building things we can barely imagine. Tiny, heavy, and terrifyingly real. Of all the gas giants, Saturn is the showstopper. With its dazzling rings, dozens of moons, and enormous storms, it's one of the most recognizable and surreal-looking objects in the solar system. But here's a fact that seems like a joke, and yet it's absolutely true. If you could drop Saturn into a giant bathtub full of water, it would float. Yep, the second largest planet in the solar system is so low in density, it's less dense than water. Let's break this down. The numbers don't lie. Saturn's average density is about 0.687 grams per cubic centimetre. Water's density is 1 gram per cubic centimetre. So on average, Saturn is less dense than water, which by the rules of buoyancy means it would float if submerged. In fact, Saturn is the only planet in our solar system with this distinction. Jupiter, too dense. Neptune, heavier still. Earth, way denser. But Saturn, the giant, the gas balloon, would bob like an enormous pale yellow beach ball, if of course we could find a water tank 75,000 miles wide and deep enough to fit a planet, which we can't. But let's imagine anyway. So, why is Saturn so puffy? It all comes down to composition. Saturn is made mostly of hydrogen and helium, the two lightest elements in the universe. These gases don't weigh much, even when there's a lot of them. Now, Saturn is still massive. It's 95 times the mass of Earth and more than 9 times our diameter. But all that mass is spread out across a huge gassy envelope, with a small dense core buried far beneath the clouds. That means most of Saturn is fluff, at least in planetary terms. It's like a marshmallow next to a bowling ball. It takes up a lot of space, but it's light compared to its size. Would it really float? Well, yes, but it's more of a thought experiment than an actual testable claim. In reality, Saturn doesn't have a solid surface. It's held together by its own gravity, not by anything solid like rock or metal. If you dropped it into water, ignoring physics for a moment, it would probably compress due to pressure, or dissolve into a weird mix of hydrogen, helium, and liquid. So, no, Saturn wouldn't behave like a literal rubber ducky. But from a pure density standpoint, it passes the buoyancy test. And that's what makes this fact so delightful. A planet with rings large enough to span nearly 1 million kilometres. A planet with more than 80 moons. A planet that could fit 764 Earths inside it. Would float. Why does this matter? Because it reshapes how we think about planets. Big doesn't always mean dense. Massive doesn't always mean heavy. In space, composition is everything. Saturn's low density tells us about its formation, its chemistry, its atmosphere, and even helps astronomers detect exoplanets around other stars by comparing lightness, size, and orbital behaviour. And it's a reminder that the universe often looks one way, but behaves another. Something as huge and intimidating as Saturn turns out to be light enough to ride the waves. If only we had a sea big enough. When we talk about big numbers, our minds usually go to things like stars, galaxies, or maybe grains of sand on Earth. But sometimes, the most mind-blowing scales aren't cosmic, they're microscopic. So here's a fact that sounds fake but is absolutely real. There are more molecules in a single cup of water than there are stars in the entire observable universe. Yes, in that one small glass on your desk. Let's do the numbers. First, the stars' estimates of the number of stars in the observable universe range from 100 billion trillion to 200 billion trillion. In scientific notation, that's around 10 to 23 to 2 test 24 stars. That's a staggering number. It's impossible to visualize. You'd have to count for millions of years just to say all the digits. But now let's look at your cup of water. Now, the molecules a standard cup of water is about 250 milliliters. That's 0.25 liters. Water's molecular formula is H2O, and each molecule is tiny, weighing about 18 atomic mass units. Using Avogadro's number, which tells us that 1 mole of any substance contains about 6.0722 x 1023 particles, we can calculate the number of molecules in that cup. In 250 ml of water, there are roughly 13.9 moles of water. Multiply that by Avogadro's number, 13.9 stick x, 6.022 1023. 8.37 x 1024 molecules. That's more than 8 septillion molecules, or over 8,000. That's already more than the number of stars in the observable universe, and that's just one glass of plain old water. What does that mean? It means that the universe of the very small is just as overwhelming as the universe of the very large. When you drink a glass of water, you're interacting with a literal galaxy's worth of molecules. And if you were to somehow magically label each H2O molecule with a name, you'd need more names than stars in existence. Even more amazing, those molecules are constantly recycled. The water in your cup may have once passed through a dinosaur's gut, a thundercloud over ancient Africa, or a glacier from the last ice age. And now those same molecules are swirling in your tea or coffee or water bottle, still numbering in the septillions, dancing to the laws of quantum physics, bouncing off each other billions of times per second. Scale is deceptive. We tend to think that big's just outer space, but the molecular scale, it laughs at that assumption. The number of water molecules in a single drop, just a drop, is roughly 1.5 sextillion, 1.5 risks 1021. That's still more than the number of grains of sand on every beach on Earth. So we live in a strange kind of cosmic symmetry. Look up, and you're overwhelmed by the vastness of space. Look down, and you're overwhelmed by the vastness inside matter itself. And that little glass on your table, it holds more than the sky. The moon feels constant, a nightly companion. Same face, same glow, same orbit. You look up, and there it is, as if it's always been there, and always will be. But the truth is stranger, because the moon is slowly drifting away from Earth, about 3.8 centimetres, or roughly 1.5 inches every single year. That might not sound like much, but it adds up, and it reveals something profound about the hidden dance between Earth and its only natural satellite. How do we know? In 1969, Apollo astronauts placed reflectors on the moon's surface, shiny panels that bounce back laser beams aimed at them from Earth. Scientists have been pinging the moon ever since. By measuring the time it takes for a laser to travel to the moon and back, with millimeter precision, we've discovered that the moon is steadily moving away from us. And it's been doing that for billions of years. Why is the moon drifting? The short answer: tides. The gravitational pull between Earth and the moon creates bulges in Earth's oceans, what we experience as high tides. But Earth rotates faster than the moon orbits, which causes the tidal bulge to shift slightly ahead of the moon. That bulge pulls on the moon gravitationally, giving it a little boost, like a gravitational slingshot. Over time, that energy transfer causes the moon to move farther away and Earth's rotation to slow down. That's right. Not only is the moon drifting, but our days are getting longer too, around 1.7 milliseconds longer per century. Tiny now, but significant over geologic time. What does that mean over time? Right now, the moon is about 384,400 kilometers, 238,655 miles away. But 1.4 billion years ago, it was much closer. A year had more days, and each day was only about 18 hours long. In another 600 million years, the moon will have drifted far enough away that total solar eclipses, those perfect alignments where the moon covers the sun exactly, will no longer be possible. The moon will appear too small in the sky. Eventually, Earth and the moon will reach a state of tidal lock with each other, not just the moon always showing one face, as it does now, but Earth doing the same in return. One side of Earth would forever face the moon, while the other would never see it. That's billions of years away. But the process is happening right now. Is this dangerous? Not at all. At least not in any human time frame. The drift is slow, predictable, and even scientifically useful. It helps us understand Earth's history, the evolution of the solar system, and the delicate gravitational choreography between celestial bodies. A moving moon. The moon's drift reminds us that the sky is not fixed. We live in a universe of motion. Slow, patient, but relentless. Every time you look up at the moon, you're seeing it just a little farther than the last time. And millions of years from now, someone else might look up and see a smaller moon in the sky. Slightly dimmer, a little more distant, and part of a very long goodbye. It won't vanish, but it will change. Because even the moon is on the move. When we think about the solar system, we tend to picture the planets first. Jupiter with its storms, Saturn with its rings, Earth with its life. But all of that is just detail work compared to the main act. Because the sun doesn't just sit at the centre of the solar system, it is the solar system. In terms of mass, it dominates everything. The sun makes up an astonishing 99.8% of the total mass of our entire solar system. All the planets, moons, asteroids, comets, dust, rings, and every little grain of matter you've ever heard of, they account for just 0.2%. And of that 0.2%, more than 70% is just Jupiter. Earth? A literal rounding error. The sun is a vast ball of hydrogen and helium, 1.4 million kilometers wide, weighing roughly 30 kilograms. It contains enough mass to fit about 330,000 Earths inside it. And it's not just massive, it's powerful. Its gravity controls everything. It keeps planets locked in orbits, governs the behaviour of comets and asteroids, and even influences the edge of the heliosphere, where solar wind meets interstellar space. When the sun sneezes, the solar system flinches. A single solar flare can release more energy than every nuclear bomb on Earth combined. Its fusion core converts over 600 million tons of hydrogen into helium every second, emitting light and heat that powers life across a 100 million mile distance. And it's been doing that for 4.6 billion years. What's especially wild is how the sun's dominance goes unnoticed. We see it every day, or at least its light. But it's easy to forget it's a star, a colossal fusion reactor, endlessly boiling, constantly shaping the space around it. We call everything else space, but the sun fills it with radiation, particles and gravity. Even beyond Pluto, its influence stretches. The outer reaches of the solar system, the Kuiper belt, the Oort cloud, all are still tethered to the sun's gravity. In fact, the Oort cloud may extend nearly halfway to the next star. The sun's hold is that vast, it's also mortal. One day, in about 5 billion years, the sun will exhaust the hydrogen in its core, swell into a red giant, possibly swallowing Mercury, Venus and maybe even Earth. Then, it will shed its outer layers and settle into a white dwarf, no longer fusing atoms but still glowing with residual heat for trillions of years. But for now, it remains the engine of the solar system. Not just the light source, but the anchor, the furnace, the mass. So next time someone tells you we live in a system of planets orbiting a star, you can gently correct them. We live in a star with a few pebbles caught in its gravity. The solar system isn't planets with a sun, it's the sun with a little extra. When we look up at the night sky in the northern hemisphere, there's a comforting constant. Polaris, the North Star. It marks due north, anchoring the sky while everything else seems to spin around it. It's been a navigational guide for sailors, explorers and stargazers for centuries. But here's the twist. Polaris hasn't always been the North Star, and it won't be forever. In fact, in the far future, Earth will have not just a different North Star, but at one point it will have two of them, close enough in the sky that they'll share the title. It's all because of a slow, graceful wobble in Earth's axis called precession. Picture a spinning top. When it spins perfectly, its tip stays still, but as it starts to wobble, that tip traces a circle. Earth does the same thing. Over a cycle of about 26,000 years, Earth's rotational axis slowly traces a circle in the sky. This precession means that the direction north points to changes gradually over millennia. Right now, our north axis points very close to Polaris. But 5,000 years ago, it pointed toward a different star, Thuban, in the constellation Draco. And 12,000 years from now, it will aim near Vega, one of the brightest stars in the sky. But between now and then, something unusual will happen. Roughly 4,000 years from now, Earth's axis will point between two bright stars, Polaris and its near-sky neighbour, Eris, also known as Gamma Cephei. During this period, both stars will be close enough to the celestial North Pole that they'll appear to share the role of North Star. To observers on Earth, the two stars will take turns being closest to true north, creating a rare era of dual pole stars. It won't be a sudden switch or dramatic change, just a slow drift year by year as the axis glides between celestial markers. What makes this even more fascinating is that this phenomenon isn't rare in astronomical terms. It's happening on a regular cycle. Every few thousand years, a new star inherits the role of north. Vega has done it, Thuban did it, Polaris is doing it now, and eventually others will follow. The South Pole has its own story too. Right now, it doesn't point to any prominent star, but that will change over time as well. It's like the sky is breathing in slow motion, gently shifting the map of constellations as the centuries pass. For most people, Polaris seems eternal, but from the universe's point of view, it's just the latest actor in a long-running play. What we think of as a fixed point in the sky is actually a moving target, part of a celestial cycle that outlasts civilizations. One day, stargazers will point upward and say, "There's the north, between those two stars," and they'll be right. Earth's axis will be aiming between Polaris and Eris, and for a time, both will shine as our double beacons in the north. The night sky may seem still, but it moves, slowly, silently, and one day it will give us two North Stars instead of one. Galaxies are supposed to be made of stars, that's the deal. You look at one through a telescope and you see a glowing spiral or elliptical shape, billions or even trillions of stars swirling together in gravitational harmony. But then along comes a discovery that flips that idea on its head. Some galaxies don't appear to have any stars at all, just dark matter, invisible galaxies. That's not science fiction, that's modern astronomy. In 2018, astronomers using the Dragonfly telephoto array observed a peculiar galaxy called NGC 1052 DF2. It's located about 65 million light-years away, and what made it shocking wasn't what it had, it's what it lacked. It barely had any stars. In fact, it seemed to have almost no detectable dark matter either. That's weird enough. But then came more discoveries. Galaxies like DF4 and others in the same class began to show similar characteristics. Enormous, ghostly clouds with very few stars, no bright centres, and little of the structure we expect. These are called ultra-diffuse galaxies. They're roughly the size of the Milky Way, meaning hundreds of thousands of light-years across, but they have less than 1% the number of stars. That's like spreading the entire population of a major city across a continent. You'd barely see anyone. They're almost transparent. Some of them are so faint they weren't discovered until recently because they don't emit enough light to stand out. But then, scientists found another twist. Galaxies that seem to have no stars at all, just massive amounts of dark matter. Now, dark matter is already one of the greatest mysteries in physics. It doesn't emit light, it doesn't absorb it. We can't see it directly, but we know it's there because of its gravitational effects. Most galaxies are surrounded by halos of dark matter that help hold them together, but some galaxies appear to be made almost entirely of it, with little or no visible matter at all. These so-called dark galaxies have been theorized for decades, but now we're starting to get glimpses of them through indirect measurements, like how they bend light from objects behind them, or how they interact with neighbouring galaxies. It's like spotting a ghost by watching the curtains move. One candidate is Virgo He21, a cloud of hydrogen gas with galaxy-like mass but no visible stars. Based on how fast its gas is spinning, it seems to be gravitationally bound by something, and that something isn't shining. Another possible explanation? These galaxies may have failed to form stars due to extreme conditions, perhaps a lack of cold gas, or some early cosmic event that stunted their growth. They might have formed in regions of space where matter was too spread out, or they could be the stripped cores of once brighter galaxies, torn apart by interactions with larger neighbours. Whatever the cause, the idea that a galaxy, something we define by its shining stars, could exist without any visible stars at all is deeply weird. And yet, it fits the math. It fits the models. And it fits the strange truth we keep learning over and over in astronomy. That what you can't see often tells the bigger story. So the next time you look up at the stars and marvel at the galaxies you can see with your eyes, or through telescopes, remember, there are likely just as many out there that are completely invisible. Galaxies made of mystery, drifting through space, shaped by something we still don't fully understand. They don't shine, but they're there, watching the universe in silence. It sounds poetic, the kind of thing you'd expect to hear in a song or a sentimental quote. But it's not just metaphor, it's science. You, me, everyone you've ever known, and everything you've ever touched is made of stardust. Literally. The atoms in your body, carbon, nitrogen, oxygen, calcium, iron, all of them were forged in the hearts of ancient stars that lived and died billions of years ago. The hydrogen in your body is older than the Earth itself, formed just minutes after the Big Bang. But everything else, all the heavier elements, came from stars. Here's how it works. Stars are essentially giant nuclear furnaces. In their cores, they fuse hydrogen into helium. As they age, the bigger ones go on to fuse helium into carbon, carbon into oxygen, and so on, building up heavier and heavier elements like a cosmic forge. But they can't make everything. To create elements heavier than iron, you need something even more powerful, a supernova. When a massive star runs out of fuel, it collapses under its own gravity and explodes in one of the most energetic events in the universe. That explosion doesn't just destroy the star, it creates a flood of neutrons, slamming them into atoms and forging elements like gold, silver, uranium, and platinum. Those elements are scattered across space. Over time, they mix with gas clouds, collapse under gravity, and form new stars, planets, and eventually people. That iron in your blood, it came from a supernova. The calcium in your bones, a dying star gave that to you. The oxygen in your lungs, forged in stellar fusion. You're not only made of stars, as you are the product of multiple generations of stars. The Milky Way has gone through billions of years of stellar births and deaths to create the elements that now make up our world. Even more mind-blowing, the exact mix of elements in your body is a kind of cosmic fingerprint. You're mostly oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus, the same 6 elements found in almost all life on Earth. And those elements aren't special to Earth. They're abundant throughout the universe. The recipe for life is not unique. The universe has been making this stuff for billions of years. That's why, when astronomers study the light from distant stars and galaxies, they find the same ingredients, the same atomic fingerprints, scattered across the cosmos. It means that what's in you is not rare, it's universal. You are part of the universe's ongoing chemical evolution, a walking, thinking, stardust-based life form. And that's not an exaggeration or a feel-good metaphor, it's fact. Carl Sagan popularised the phrase, and for good reason. It's one of the most profound truths we've discovered. The universe didn't just create the stars created us. So when you look up at the night sky, you're not looking at something separate, you're looking at your own history. Your atoms once burned in the cores of suns, your elements were scattered across space by stellar winds and supernovae. And now they've come together, briefly, miraculously, in the form of you. Eventually those atoms will go back into the cosmos, and the cycle will continue, stardust to stardust, always.